In the late 1970s, two small spacecraft left Earth on a journey unlike any other. Their names were Voyager 1 and Voyager 2, and their mission was to explore the outer planets of our solar system and then venture into the vast, uncharted space beyond. Decades later, these twin probes are still out there, quietly traveling through the darkness, billions of miles from home. They've become humanity's farthest messengers, carrying with them not just scientific instruments, but also a golden record of Earth, a time capsule meant for anyone or anything that might one day find it. What have they seen out there, at the edge of the solar system and beyond? What secrets of the cosmos have they uncovered in the quiet, empty vastness of interstellar space? Genesis of the Voyager program, a bold vision for the cosmos. In the early 1970s, the Apollo program had reached its climax, leaving footprints on the Moon. But the question remained, what lay beyond? Scientists and engineers began to dream of missions that could venture further than ever before into the vast expanse of the solar system. Among these dreams was the bold vision that would eventually become the Voyager program, a mission designed to unlock secrets of the outer planets and perhaps even touch the stars. The seeds of this ambitious endeavor were sown in the minds of a small but determined group of visionaries. They were inspired by a unique celestial alignment that would occur in the late 1970s, a once-in-176-year event. This alignment would allow a spacecraft to use the gravitational pull of the giant planets, Jupiter, Saturn, Uranus, and Neptune, to slingshot from one to the next, drastically reducing the energy required for such a journey. The concept, known as a gravity assist, was not new, but this rare alignment made it possible to explore the outer planets in a single mission, a feat previously deemed unachievable. The challenge, however, was immense. Designing a spacecraft capable of traveling billions of miles, enduring the harsh environment of space, and continuing to function for years, or even decades, was an incredible undertaking. The engineers and scientists at NASA's Jet Propulsion Laboratory, or JPL, were undeterred. They recognized that the alignment presented an opportunity that would not come again for generations. The spacecraft needed to be not only robust, but also capable of adapting to unforeseen challenges. They designed systems that could diagnose and repair themselves, a necessity for a mission that would travel far beyond the reach of real-time human intervention. The spacecraft would carry redundant systems, ensuring that a single failure would not spell the end of the mission. Every detail, from the radiation shielding to the long-lasting power sources, was meticulously planned. Solar panels, the standard power source for many spacecraft, would be useless in the dim outer reaches of the solar system. Instead, the engineers turned to radioisotope thermoelectric generators, or RTGs, which convert the heat from the decay of plutonium-238 into electricity. These RTGs were not only reliable, but also capable of providing power for decades, a necessity for a mission of such unprecedented duration. Voyager was designed to be a scientific powerhouse equipped with cameras, spectrometers, and detectors to study the planets, their moons, and the surrounding environment. Each instrument had to be lightweight, energy efficient, and capable of withstanding the rigors of space travel. The data these instruments would collect promised to revolutionize our understanding of the outer planets, providing insights into their atmospheres, magnetic fields, and geological features. As the spacecraft ventured farther from Earth, the time it took for signals to travel back and forth would increase, eventually reaching hours. This delay meant that Voyager had to be semi-autonomous, capable of making decisions on its own. The spacecraft would also need a powerful antenna to transmit data across billions of miles. Engineers designed a high-gain antenna, a dish that could beam information back to Earth with remarkable precision. While its primary mission was to explore the outer planets, the spacecraft were also designed to serve as ambassadors of humanity. Each Voyager carried a golden record, a time capsule intended for any extraterrestrial beings who might one day encounter the spacecraft. The record contained sounds and images from Earth, a snapshot of life on our planet. This inclusion was a testament to the program's audacity and optimism, a recognition that Voyager's journey would continue long after its scientific mission was complete. The people behind the program were acutely aware of the stakes. They knew that a single miscalculation or oversight could doom the mission. Yet they also knew that the potential rewards were enormous. Voyager represented humanity's desire to reach beyond the familiar, to explore the unknown, and to leave a mark on the cosmos. A grand tour navigating the outer planets. The concept of using gravity assists, also known as slingshots, was central to the mission's success. The idea was simple in theory, but complex in execution. As the spacecraft approached a planet, the planet's gravity would pull it in, increasing its speed. By carefully timing its approach and trajectory, the spacecraft could then use this added momentum to slingshot away from the planet and onto its next target. This technique not only saved enormous amounts of fuel, but also made it possible for Voyager to travel the vast distances between the outer planets in a relatively short amount of time. Jupiter was the first major stop on Voyager's journey, and it played a critical role in the mission. The planet's immense gravity provided the first and most significant boost to the spacecraft. To take full advantage of this, engineers had to calculate Voyager's trajectory with extraordinary precision. Even a slight error in the spacecraft's path could have sent it hurtling into space, missing its targets entirely. But the team's calculations were flawless, and Voyager was able to pass close enough to Jupiter to gather groundbreaking data while still maintaining the perfect trajectory for the next leg of its journey. The encounter with Jupiter was a milestone not only for the mission, but also for space exploration as a whole. Voyager's instruments captured stunning images of the planet's swirling atmosphere, revealing details that had never been seen before. The spacecraft also flew close to Jupiter's largest moons, including the volcanic Io and the icy Europa, providing the first up-close views of these mysterious worlds. Each discovery added to the growing sense of wonder and excitement surrounding the mission. Saturn was the next stop, and it presented its own set of challenges and opportunities. Like Jupiter, Saturn's gravity was used to propel Voyager further into the solar system. But Saturn was more than just a stepping stone. Its iconic rings and diverse moons offered a treasure trove of scientific data. Voyager's instruments revealed the intricate structure of the rings, uncovering details that had eluded astronomers for centuries. The spacecraft also made a close pass by Titan, Saturn's largest moon, which was shrouded in a thick atmosphere of nitrogen and methane. This encounter provided tantalizing clues about the moon's surface and composition, sparking questions that would later lead to the Cassini-Huygens mission. By the time Voyager left Saturn, it had already exceeded expectations, but the mission was far from over. For Voyager 2, the journey continued to Uranus and Neptune, two planets that had never been visited by spacecraft before. Uranus, with its pale blue-green hue and tilted axis, revealed a strange and icy world, while Neptune, the final planet in this grand tour, showcased deep blue storms and the supersonic winds of its atmosphere. Each encounter required months of planning and preparation, as well as split-second timing, to ensure that the spacecraft passed at the right distance and angle to collect the most valuable data. The gravity assists themselves were a delicate balance of physics and precision, with even the smallest miscalculation carrying the risk of disaster. Yet time and again, Voyager met these challenges, navigating the outer planets with a level of accuracy that seemed almost miraculous. Each flyby added to the wealth of knowledge about the solar system, providing insights that would shape our understanding of the universe for decades to come. The images and data sent back by Voyager were not just scientific achievements. They were glimpses into worlds that had once been little more than points of light in the night sky. Once Voyager had completed its tour of the planets, it would continue its journey, heading into the vast and uncharted territory of interstellar space, pioneering beyond expectations, engineering for the unknown. When the Voyager program was conceived, its creators knew they were venturing into uncharted territory. The spacecraft would be traveling farther than any human-made object had before, into regions of space where conditions were harsh and unpredictable. To succeed, Voyager had to be more than just a collection of scientific instruments. It had to be a masterpiece of engineering. It needed to survive extreme radiation, endure freezing temperatures, and function for years without direct intervention. Spacecraft designed for earlier missions, such as the moon landings or Mars flybys, were built for relatively short durations and operated within environments that, while challenging, were somewhat familiar. Voyager, by contrast, would need to survive decades in space, moving through regions bombarded by cosmic radiation and far from the warming light of the sun. It would need to operate autonomously, diagnosing and solving problems on its own. This required innovations that pushed the boundaries of technology at the time. Radioisotope thermoelectric generators, or RTGs, convert heat from the radioactive decay of plutonium-238 into electricity, providing a steady and reliable power source. RTGs were not only long-lasting, but also remarkably durable, capable of withstanding the cold and radiation of deep space. Without them, Voyager's journey would have been impossible. The spacecraft was equipped with a high-gain antenna, a large dish designed to send data back to Earth with incredible precision. Even so, the signals reaching Earth would be faint, requiring sensitive receivers on the ground to pick them up. The engineers also had to account for the increasing time delay as Voyager moved farther away. Commands sent from Earth would take hours to reach the spacecraft, so Voyager needed the ability to operate independently. Its onboard computers, though primitive by today's standards, were programmed to handle routine tasks and respond to unexpected events without waiting for instructions from Earth. The spacecraft carried a suite of tools to study the planets, moons, and environment it encountered. These included cameras for imaging, spectrometers for analyzing light, and detectors for measuring magnetic fields and charged particles. Each instrument had to be compact, lightweight, and energy efficient. They also needed to be protected from the harsh conditions of space. Engineers used a combination of insulation and shielding to ensure that the instruments would continue to function, even in the face of intense radiation or extreme cold. The spacecraft was built with multiple backups for critical systems, ensuring that a single failure would not jeopardize the mission. For example, Voyager had 3 identical computers on board, each capable of taking over if the others failed. Its attitude control system, which kept the spacecraft properly oriented, was equipped with duplicate components. Even the communication system had redundant pathways, allowing Voyager to continue transmitting data even if part of the system was damaged. The spacecraft was built to last 5 years, long enough to complete its primary mission of exploring Jupiter and Saturn. Yet the engineers had the foresight to include features that would allow it to continue operating far beyond this time frame. Voyager's systems were designed to be reprogrammable, a groundbreaking concept at the time. Over the years, NASA has been able to send software updates to the spacecraft, allowing it to adapt to new challenges and take on new objectives. This ability to evolve has been crucial to Voyager's longevity. One example of this adaptability is the way Voyager has managed its power supply. As the plutonium in its RTGs decays, the spacecraft generates less electricity. To conserve power, engineers have gradually turned off non-essential systems, prioritizing the instruments and functions that are most important to the mission. This careful management has allowed Voyager to continue sending valuable data, even as its power levels decline. During its journey through the outer planets, the spacecraft encountered intense radiation near Jupiter, frigid temperatures near Uranus and Neptune, and countless tiny particles that could have damaged its instruments. Yet it has endured, thanks to the robust engineering and meticulous planning that went into its design. Even in the vast emptiness of interstellar space, where temperatures approach absolute zero and cosmic rays bombard the spacecraft, Voyager continues to operate, a testament to its durability. A symphony of data. The Golden Record's scientific implications. The Voyager spacecraft carried more than just scientific instruments. It carried a message, a record of Earth and its people, carefully designed to communicate the essence of humanity to any extraterrestrial civilization that might encounter it. This message was etched onto the Golden Record, a gold-plated copper disc containing sounds, images, and music from our planet. The idea for the Golden Record came from Carl Sagan and his team, who envisioned it as a time capsule. They knew the chances of an alien civilization finding the record were vanishingly small. The real audience was humanity itself, a way to capture a snapshot of life on Earth at a particular moment in time. It was a bold statement of who we are, what we know, and what we value. The record begins with a greeting, a universal salutation designed to reach across the barriers of time, space, and language. It includes spoken messages in 55 languages, each offering a simple hello or a wish for peace. These greetings are a reminder of the richness of human culture, reflecting a world where countless languages and traditions coexist. Alongside these are sounds of Earth, waves crashing, birds singing, thunder rolling. These sounds are meant to convey the essence of our planet, a symphony of life and nature. Music plays a central role on the Golden Record, representing humanity's creativity and emotion. The selection spans a wide range of cultures and traditions, from Bach and Beethoven to traditional music from Africa, Asia, and the Americas. Each piece was chosen not just for its beauty, but for its ability to express something universal about the human experience. The music is a bridge, a way of communicating feelings that transcend language. The record also contains a collection of images, encoded in analog form. These images depict a wide variety of subjects, people of different cultures, animals, plants, landscapes, and even diagrams of our solar system and DNA. Each image was carefully selected to provide a glimpse into life on Earth, from the microscopic to the cosmic. The images were designed to be decoded by an intelligent observer, with instructions included on how to reconstruct them from the signals on the record. The team included detailed information about Earth and its inhabitants, from the chemical composition of our atmosphere to the structure of our DNA. There are diagrams showing the location of our solar system relative to 14 pulsars, a kind of cosmic map to help extraterrestrial beings locate Earth. The record also includes a depiction of human anatomy and instructions for playing the disc, complete with the speed and method of playback. The inclusion of scientific data on the Golden Record was a deliberate choice. It was a way of demonstrating humanity's technological achievements and our understanding of the universe. Pulsars are highly regular sources of radio waves, making them reliable cosmic landmarks. By including the unique frequencies of these pulsars, the record provides a kind of interstellar address, a way for future finders to trace the record's origin. The scientific content also reflects humanity's curiosity and humility. It acknowledges that we are part of a larger universe, a small planet orbiting an average star in one galaxy among billions. By sharing our knowledge, the record invites others to learn about us, to see us as we see ourselves. It is both a declaration of our existence and an invitation to connect. The sounds of animals, the images of plants, and the recordings of human voices all testify to the incredible variety of life on our planet. This diversity is one of Earth's defining characteristics, a reminder of the complex web of life that sustains us. By including these elements, the record celebrates the richness of our world and highlights the importance of preserving it. Scientists, artists, musicians, and linguists all contributed to its content. The process of selecting what to include was both a challenge and an opportunity, forcing the team to think deeply about what defines humanity and what we would want others to know about us. Every choice was a compromise, a balance between what was possible and what was meaningful. The 1970s were a time of optimism about space exploration, a period when humanity was just beginning to venture beyond its home planet. The record captures this spirit of exploration, and the belief that our efforts to understand the cosmos could lead to profound discoveries. It is a message of hope, a symbol of what humanity can achieve when it works together. While the golden record is unlikely to be found by extraterrestrial beings, it serves as a reminder of our shared humanity, a way of seeing ourselves from an outside perspective. It challenges us to think about what we value and how we represent ourselves to others. In many ways, the record is as much about the future as it is about the present, a message to future generations about who we were and what we aspired to be. Jupiter's Tempest – Insights from the First Flyby. As Voyager approached Jupiter, the excitement among scientists was palpable. This was the first of the outer planets to be explored by the spacecraft, and the largest planet in the solar system promised to reveal mysteries that had puzzled astronomers for centuries. Jupiter had always been an object of fascination, its swirling bands of clouds and the enormous Great Red Spot, visible even through modest telescopes. But now, for the first time, humanity would see the giant planet up close, in detail that was previously unimaginable. Voyager's instruments began capturing data well before the spacecraft reached its closest approach. Its cameras sent back images of Jupiter's atmosphere, revealing a world of breathtaking complexity. The planet's iconic bands of clouds, known as zones and belts, were not just simple stripes. They were dynamic, turbulent systems of winds and storms. The zones, lighter in color, were found to be regions of rising air, while the darker belts were areas where air sank back down. These bands moved in opposite directions, creating powerful wind systems that wrapped around the planet. The Great Red Spot, a feature that had been observed for over 300 years, came into sharper focus than ever before. We learned that the spot was a massive storm, larger than the Earth, with winds swirling at hundreds of miles per hour. It was a high-pressure system, unlike the low-pressure systems that dominate storms on Earth. Scientists were fascinated by its longevity. How could a storm persist for centuries? The data suggested that Jupiter's lack of a solid surface allowed storms like the Great Red Spot to avoid the friction that would dissipate them on a terrestrial planet. The immense energy provided by Jupiter's internal heat also fueled these storms, making them incredibly powerful and long-lasting. Voyager's instruments also detected smaller storms scattered across Jupiter's atmosphere. These storms appeared as white ovals or dark spots, each with its own swirling winds and complex structure. Some of these storms interacted with each other, merging or splitting apart in dramatic displays of atmospheric dynamics. These observations showed that Jupiter's atmosphere was far more active and chaotic than previously understood, a world in constant motion. Another discovery came from Voyager's ultraviolet and infrared instruments, which observed Jupiter's auroras. These shimmering lights, similar to the northern and southern lights on Earth, were caused by charged particles interacting with the planet's magnetic field and atmosphere. But Jupiter's auroras were far more intense and complex than Earth's. They formed near the poles, where Jupiter's powerful magnetic field funneled particles from the solar wind and the planet's own magnetosphere into the upper atmosphere. The energy released in these interactions created dazzling displays of light, stretching thousands of miles across the planet. Voyager also revealed that Jupiter's magnetic field was much stronger than previously thought. This magnetic field, the largest in the solar system, trapped charged particles in immense radiation belts that encircled the planet. These radiation belts posed a significant hazard to the spacecraft, but Voyager's robust design allowed it to withstand the intense environment and continue its mission. The data collected from these regions provided valuable insights into the interactions between Jupiter's magnetic field and its atmosphere, as well as the effects of the solar wind on the gas giant. Voyager also captured data on the planet's composition. The atmosphere was found to be mostly hydrogen and helium, with trace amounts of other elements like methane, ammonia, and water vapor. These findings confirmed that Jupiter was similar in composition to the Sun, supporting the idea that it had formed from the same primordial cloud of gas and dust that created the solar system. The planet was radiating more heat than it received from the Sun, a discovery that hinted at an internal heat source. This heat was likely left over from Jupiter's formation, when the planet's immense gravity compressed its core, releasing energy in the process. The internal heat played a significant role in driving the atmospheric dynamics observed by Voyager, fueling the planet's storms and wind systems. As Voyager passed by Jupiter, it also captured stunning images of the planet's thin ring system. Unlike Saturn's bright and extensive rings, Jupiter's rings were faint and composed of small particles, likely debris from impacts on its moons. The discovery of these rings was a surprise, as they had been undetectable from Earth. Voyager's observations showed that ring systems might be more common around planets than previously thought, sparking interest in studying the rings of other gas giants. Jupiter was no longer seen as a simple static world, but as a dynamic and complex system. Its atmosphere, magnetic field, and auroras revealed processes that were unlike anything seen on Earth, expanding our knowledge of planetary science. The flyby also demonstrated the incredible capabilities of the Voyager spacecraft, proving that it could not only survive the challenges of space, but also provide groundbreaking insights into the planets it explored. Io's volcanic fireworks, a surprising discovery. After speeding past Jupiter, Voyager 1 turned its instruments toward Io, one of the planet's 4 largest moons. At first glance, Io seemed like a strange, colorful world. Its surface was covered in patches of yellow, orange, and white, unlike the dull, cratered surfaces of many other moons. Scientists expected Io to be geologically inactive, much like Earth's moon. What they found instead would rewrite the understanding of astrogeology. The first hint that Io was different came from its lack of impact craters. Other moons in the solar system bore the scars of countless collisions with asteroids and comets, their surfaces pockmarked with craters that had endured for billions of years. Io, however, was almost pristine. Its surface appeared fresh, as if something was constantly renewing it. The data puzzled scientists, but the answer soon became clear in a dramatic and unexpected way. As Voyager 1's cameras captured images of Io's limb, they revealed a sight that stunned the mission team. A massive plume of material was erupting from the moon's surface, reaching hundreds of kilometers into space. This was a volcanic eruption, the first ever observed beyond Earth. The plume was composed of sulfur and sulfur dioxide, materials that gave Io its colorful appearance. It was a discovery no one had anticipated, a revelation that turned Io into one of the most geologically fascinating objects in the solar system. Further analysis of Voyager's data showed that this eruption was not an isolated event. Io was covered with active volcanoes, some of which were visible as bright spots in infrared images. These volcanoes were unlike those on Earth. Instead of spewing molten rock, they erupted with sulfur compounds. The volcanic activity was so intense that Io's surface was constantly being reshaped, with lava flows covering old terrain and creating new features. Io orbits closer to Jupiter than any of the other large moons, placing it in a region where the planet's immense gravity exerts a powerful tidal force. These tidal forces are not constant. They are influenced by the gravitational pulls of Europa and Ganymede, the 2 other large moons in the system. This interaction creates a phenomenon known as tidal heating. As Io orbits Jupiter, the varying gravitational forces stretch and compress the moon, generating heat through friction within its interior. This heat is so intense that it melts Io's interior, creating reservoirs of molten sulfur and silicate rock. The molten material rises to the surface through cracks and vents, driving the moon's relentless volcanic activity. Tidal heating had been theorized before, but Voyager's discovery of active volcanism on Io provided the first clear evidence of its effects. The volcanic activity on Io demonstrated that even small celestial bodies can be geologically active if they are subjected to the right conditions. It also highlighted the importance of tidal forces in shaping the characteristics of moons and planets. Io's volcanism was a vivid example of how gravitational interactions can create energy and drive dramatic changes on a planetary scale. Voyager's observations also revealed that Io's volcanic eruptions were not just a surface phenomenon. The material ejected by its volcanoes contributes to a complex system of interactions between the Moon and Jupiter. The sulfur and sulfur dioxide particles from Io's eruptions form a thin atmosphere around the Moon. Some of this material escapes into space, creating a vast torus of plasma that encircles Jupiter. This plasma torus interacts with Jupiter's powerful magnetic field, creating auroras and influencing the planet's magnetosphere. The material ejected from Io can also reach the surfaces of Europa and Ganymede, creating a dynamic environment of particle exchange between the moons. This interconnected system is a reminder of how closely linked the bodies within a planetary system can be, with processes on one moon influencing the conditions on others. The discovery of active volcanism on Io was a turning point in planetary science. It shattered the assumption that moons were cold, dead worlds, and showed that geological activity could occur under entirely different conditions from those on Earth. It also demonstrated the value of exploring the outer solar system, where surprises awaited that could not have been predicted based on observations from afar. Saturn's ethereal rings, new perspectives. Upon approaching Saturn in 1980, Voyager 1 turned its attention to one of the most iconic and captivating features in the solar system, the planet's magnificent rings. Saturn's rings had been observed through telescopes for centuries, but the detailed images and data from Voyager transformed these familiar features into a source of profound scientific discovery. The first images returned by Voyager showed the rings as a shimmering expanse of countless particles, stretching wide but only a few tens of meters thick. What appeared from Earth as solid, smooth bands were now revealed to be intricate systems of countless individual components. These particles ranged in size from tiny grains of dust to boulders as large as houses, all orbiting Saturn at different speeds. They were primarily made of water ice, mixed with traces of rocky material and organic compounds. The brightness of the rings, reflecting sunlight so brilliantly, came from the high purity of the ice. However, variations in brightness across the rings hinted at differences in particle size and composition. Some regions were darker, possibly due to contamination by meteoroid impacts or the influence of Saturn's moons. What had seemed like a simple arrangement of concentric circles was actually a complex tapestry of hundreds of distinct ringlets, each separated by narrow gaps. Some of these gaps were empty, while others contained thin, faint rings. Voyager's close-up images showed that the edges of these gaps were often sharp and well-defined, suggesting that the gravitational influence of Saturn's moons was shaping the rings. Among the most intriguing discoveries were the so-called shepherd moons, small moons that orbit near the edges of certain rings. These moons exert gravitational forces on the ring particles, confining them to narrow bands and maintaining the sharp edges of the rings. For example, the tiny moons Prometheus and Pandora were found to shepherd the particles of the F ring, one of Saturn's outermost rings. These moons acted like cosmic sculptors, their orbits creating waves, ripples, and other features in the ring material. Collisions between ring particles created temporary clumps that would eventually break apart. The gravitational interactions between the rings and Saturn's moons generated waves and other disturbances that propagated through the rings. These interactions revealed the delicate balance of forces at work, with the gravity of Saturn, its moons, and the particles themselves all playing a role in shaping the system. Another discovery was the radial features in the rings, known as spokes. These faint, ghostly streaks appeared to extend outward from the planet, cutting across the rings. The spokes seemed to defy the normal orbital motion of the ring particles, and their origin was a mystery. Voyager's data suggested that the spokes were likely composed of tiny, electrically charged particles that were lifted above the rings by Saturn's magnetic field. Voyager also captured images of the gaps within the rings, such as the Cassini division, a dark band that separates the A and B rings. The Cassini division was found to contain faint, wispy ringlets, challenging the notion that it was completely empty. The spacecraft's data showed that the gaps were not just voids, but regions where the gravitational forces of Saturn's moons created complex patterns in the ring material. The Encke gap, another notable feature, was found to host a tiny moonlet, Pan, which carved a narrow path through the ring particles. Pan's presence provided a direct demonstration of how moons and rings interact, with the moonlet's gravity creating a cleared zone and generating waves in the surrounding material. Voyager's close flyby of Saturn allowed scientists to study the outer rings in unprecedented detail. The E-ring, for instance, was found to be composed of microscopic ice particles, likely originating from the icy moon Enceladus. The data hinted at a fascinating relationship between the moon and the ring, with material from Enceladus's geysers feeding the E-ring and sustaining its ethereal appearance. The spacecraft's instruments also measured the density and mass of the rings, revealing that they contained far less material than their vast expanse might suggest. This raised questions about the rings' origin and age. Were they remnants of a moon or comet that had been shattered by a collision, or were they primordial, dating back to the formation of Saturn itself? Voyager's data could not provide a definitive answer, but it set the stage for ongoing investigations into the history of these striking structures. The images and data returned by Voyager painted a picture of Saturn's rings as a dynamic, ever-changing system. The delicate interplay of forces within the rings, the influence of shepherd moons, and the interactions with Saturn's magnetic field created a celestial symphony of motion and structure. Titan's thick shroud, a hazy enigma. Titan, Saturn's largest moon, had long intrigued scientists. It was the only moon in the solar system known to have a dense atmosphere, and its surface was hidden beneath an opaque orange veil. Voyager's mission offered a chance to peer into the unknown, and the data it sent back would forever change our understanding of this distant world. The first thing Voyager revealed about Titan was the extraordinary composition of its atmosphere. It was far thicker than Earth's, with a surface pressure about 1.5 times that of our own planet. The atmosphere was dominated by nitrogen, making it similar in composition to Earth's, but with a key difference. Methane and a mix of complex hydrocarbons made up a significant portion of the remaining gases. These hydrocarbons, formed through the interaction of sunlight with methane, gave Titan its hazy appearance and hinted at a chemistry unlike anything seen elsewhere in the solar system. Voyager's instruments detected layers of haze in Titan's atmosphere, stretching high above the surface. These layers were made of tiny particles, likely formed by chemical reactions driven by sunlight and cosmic rays. The haze absorbed and scattered sunlight, creating the moon's distinctive orange color and making direct observation of the surface impossible. This thick shroud acted as a natural laboratory where organic molecules were continuously formed and altered, mimicking processes that might have occurred on the early Earth. The hydrocarbons and other organic molecules detected by Voyager were similar to the building blocks of life on Earth. Methane, ethane, and more complex compounds were present in significant quantities, suggesting that Titan's atmosphere was rich in the raw materials needed for life to arise. Although the moon's surface was far too cold to support liquid water, with temperatures hovering around -180 degrees Celsius or -290 degrees Fahrenheit, the presence of these molecules raised questions about the chemical processes occurring in such an extreme environment. The dense atmosphere supported a dynamic system of winds and possibly precipitation. Methane played a role similar to water on Earth, existing as a gas in the atmosphere and potentially condensing into liquid on the surface. While Voyager could not directly observe rainfall or lakes, The data hinted at the possibility of methane rain and rivers, creating a landscape shaped by processes familiar yet alien. Methane is easily broken down by sunlight, meaning that it should not persist in such large quantities over geological timescales. Voyager's findings suggested that there must be a source replenishing the methane, possibly through cryovolcanism or other geological processes. This discovery hinted at an active, evolving moon, where subsurface reservoirs of methane could be venting to the surface and into the atmosphere. While Voyager could not see through Titan's thick haze to its surface, the spacecraft's instruments provided tantalizing clues about what lay beneath. Radar signals suggested that the surface was relatively smooth, with few large craters. This implied that geological or atmospheric processes were actively reshaping Titan's surface, erasing the scars of impacts over time. Voyager's data hinted at the presence of vast plains, dunes, or even liquid-filled basins, but confirmation would have to wait for future missions. While Titan was far too cold to support life as we know it, the Moon's atmospheric processes resembled a frozen analogue of the early Earth. The organic molecules present in Titan's haze were similar to those that might have existed on our planet before life began. This raised the possibility that Titan could provide a window into the prebiotic conditions that led to life on Earth, offering clues about how life might arise elsewhere in the universe. Voyager's observations also inspired questions about the potential for life in environments radically different from our own. While liquid water is considered essential for life as we know it, Titan's methane lakes and rivers suggested the possibility of alternative biochemistries. Could life exist in liquid methane, using hydrocarbons as a solvent instead of water? Voyager's data opened the door to such speculation, challenging scientists to think beyond the limits of Earth-like conditions. The Moon, once a distant and mysterious object, became a focus of intense study and fascination. Its dense atmosphere, complex chemistry, and potential for prebiotic processes made it a natural target for future missions. The data gathered by Voyager laid the groundwork for the Cassini-Huygens mission, which would later confirm many of Voyager's findings and reveal Titan's surface in stunning detail. Uranus, a tilted world in blue hues. While Voyager 1 veered off into interstellar space after visiting Titan, Voyager 2 continued its journey and approached Uranus, the seventh planet from the Sun, in 1986. Uranus, with its pale blue-green hue, appeared serene and featureless from afar, but Voyager's instruments were prepared to uncover the hidden intricacies of this enigmatic world. The spacecraft's closest flyby in January 1986 would provide humanity with its first close-up view of a planet that defied many expectations. Unlike any other planet in the solar system, Uranus rotates on its side, with an axial tilt of about 98 degrees. This means that its poles are almost in line with its orbit around the Sun. Scientists were eager to understand how such an extreme tilt affected the planet's atmosphere, seasons, and internal dynamics. Voyager's observations revealed that this unusual orientation resulted in unique seasonal variations, with one pole basking in continuous sunlight for decades, while the other was plunged into prolonged darkness. Voyager 2's instruments detected a composition dominated by hydrogen and helium, with traces of methane that gave the planet its characteristic blue-green color. Methane absorbs red light, scattering the shorter blue wavelengths and creating the planet's striking appearance. Unlike the dynamic atmospheres of Jupiter and Saturn, Uranus appeared remarkably calm, with few visible features. However, closer examination revealed subtle bands of clouds and hints of activity in the upper atmosphere, driven by the planet's internal heat and sunlight. The planet's density suggested that it was composed primarily of water, ammonia, and methane ices, mixed with rocky material. This icy composition set Uranus apart from the gas giants Jupiter and Saturn, placing it in a distinct category known as ice giants. The data gathered hinted at complex interactions between the planet's icy interior and its magnetic field. Uranus's magnetic field proved to be unlike any other in the solar system. Voyager detected a magnetic field that was both tilted at an angle of about 59 degrees relative to the planet's rotational axis and offset from the planet's center by nearly a third of its radius. This asymmetry created a highly unusual magnetic environment, with field lines twisting and warping in unexpected ways. Scientists theorized that this could be due to the unique structure of Uranus's interior, where the magnetic field might originate in a shell of electrically conducting fluids rather than in the core. The planet's magnetosphere, the region of space influenced by its magnetic field, was equally unusual. Voyager found that the magnetosphere was highly dynamic, with charged particles trapped in the field creating a complex system of radiation belts. The spacecraft also observed auroras, the result of charged particles interacting with Uranus's atmosphere. Unlike the vibrant auroras of Earth or Jupiter, Uranus's auroras were faint and irregular, shaped by the planet's tilted and offset magnetic field. The spacecraft discovered 10 previously unknown moons, bringing the total number of known satellites to 15 at the time. An 11th moon, Perdita, was also photographed, but remained undiscovered until it was pointed out by a researcher a decade later. Each of the small moons had their own unique characteristics, with some appearing to be irregularly shaped fragments of larger bodies. The 5 largest moons, Miranda, Ariel, Umbriel, Titania, and Oberon, were observed in greater detail, revealing surfaces scarred by craters, canyons, and other geological features. Miranda, the innermost of the large moons, stood out as one of the most intriguing. Voyager's images showed a patchwork of terrains, including regions with deep canyons, smooth plains, and areas covered in large ridges and grooves. The moon's surface appeared to have been reshaped by violent geological activity, possibly driven by tidal forces from Uranus. Some scientists speculated that Miranda had been shattered and reassembled multiple times in its history, creating its distinctive appearance. The flyby also revealed Uranus's faint ring system, which had been discovered a decade earlier through ground-based observations. Voyager's instruments detected 9 narrow rings composed of dark, icy particles. These rings were much darker and thinner than the rings of Saturn, and their precise composition remained a mystery. Voyager's data suggested that the rings were relatively young and possibly formed from debris left over from collisions between moons or other bodies in the Uranian system. Neptune's dynamic atmosphere wins at the edge of the solar system. Voyager 2's next destination brought it to the farthest reaches of the solar system, Neptune. This icy giant, the 8th planet from the Sun, had remained a distant and mysterious object for much of human history. Observations from Earth had hinted at a blue world with a faint system of rings, but little else was known. When Voyager 2 approached Neptune in August 1989, it offered the first close-up view of a planet whose atmosphere would prove to be one of the most dynamic and extreme in the solar system. Neptune's blue hue is caused by methane in the planet's atmosphere, which absorbs red light and scatters blue. Yet, beneath this tranquil appearance, lay a world of astonishingly intense weather. Voyager 2's instruments detected the fastest winds ever recorded on any planet, reaching speeds of up to 2,100 kilometers per hour. These supersonic winds whipped through the upper atmosphere, creating a chaotic and ever-changing environment. Neptune is located so far from the Sun that it receives only a fraction of the solar energy that drives weather systems on Earth. With such limited energy input, it seemed counterintuitive for Neptune to exhibit such powerful atmospheric activity. One theory proposed that the planet's internal heat might be a key factor. Unlike Uranus, which emits little heat, Neptune radiates more than twice the energy it receives from the Sun. This internal heat could drive convection currents within the atmosphere, fueling the high-speed winds and turbulent weather patterns observed by Voyager. Voyager's cameras captured a wealth of detail about Neptune's atmosphere, revealing a planet marked by bands of clouds and large, dark storms. The most prominent feature was the Great Dark Spot, a massive storm system similar in scale to Jupiter's Great Red Spot. The Great Dark Spot spanned roughly the size of Earth and was flanked by bright high-altitude clouds composed of methane ice crystals. These clouds, often referred to as scooters due to their rapid movement, zipped around the planet at incredible speeds. The Great Dark Spot was a dynamic feature, appearing and disappearing over time. Unlike Jupiter's more stable Great Red Spot, Neptune's storms seemed to form and dissipate on shorter timescales, reflecting the planet's constantly shifting atmosphere. Voyager also observed smaller dark spots and bright streaks, further evidence of the turbulent conditions in Neptune's skies. In addition to storms, Voyager detected a complex system of atmospheric bands. These bands, driven by the planet's rotation and high-speed winds, created a layered structure within the atmosphere. At higher altitudes, Voyager observed wispy, cirrus-like clouds composed of methane ice. Deeper within the atmosphere, scientists inferred the presence of denser layers of hydrogen and helium, along with trace amounts of other compounds. The interplay between these layers, combined with the planet's internal heat, created the dynamic weather patterns that Voyager recorded. Despite its distance from the Sun, the upper atmosphere was surprisingly cold, with temperatures dropping to around -218 degrees Celsius. However, as Voyager's instruments probed deeper, they detected warmer layers closer to the planet's core. This temperature gradient, coupled with the planet's internal heat, likely played a role in driving the powerful convection currents that fueled Neptune's extreme winds. Like Uranus, Neptune's magnetic field was tilted and offset from the planet's center, creating a highly asymmetrical magnetosphere. This magnetic environment influenced the movement of charged particles within the atmosphere, contributing to the planet's auroras. Unlike the bright and concentrated auroras seen on Earth, Neptune's auroras were diffuse and scattered, reflecting the complex interactions between the magnetic field and the solar wind. Neptune's dynamic atmosphere was not confined to the planet itself. Voyager's observations of Triton, Neptune's largest moon, hinted at atmospheric interactions between the planet and its satellite. Triton, with its thin atmosphere of nitrogen and methane, exhibited geysers that erupted from its surface, possibly driven by solar heating or tidal forces from Neptune. These geysers released plumes of gas and dust that contributed to the tenuous atmosphere around the Moon, further illustrating the interconnected nature of Neptune's system. The data collected by Voyager 2 revealed a world of extremes where supersonic winds and massive storms defied expectations about what was possible in the outer solar system. The discoveries at Neptune challenged scientists to rethink the dynamics of planetary atmospheres and raised new questions about the forces that shape weather on distant worlds. Crossing the boundary, the heliosphere's edge. As the Voyager spacecrafts ventured farther from the Sun, they began to approach a region of space that was both a boundary and a frontier, the edge of the heliosphere. The heliosphere is an enormous bubble created by the Sun's solar wind, a stream of charged particles flowing outward from the Sun in all directions. This bubble encases the solar system, shielding it from much of the interstellar radiation that permeates the galaxy. Understanding the heliosphere's structure and boundaries had been a long-standing goal of space exploration, and the Voyager was uniquely positioned to provide the first direct data from this distant frontier. The heliosphere is not a solid barrier, but rather a dynamic region where the solar wind interacts with the interstellar medium, the sparse mixture of gas, dust, and charged particles that fills the space between stars. Near the Sun, the solar wind moves outward at high speeds, forming a supersonic flow. However, as it travels farther from the Sun, the solar wind gradually slows down as it encounters the pressure of the interstellar medium. This deceleration marks the beginning of the heliosphere's outer layers, which are divided into several distinct regions. The first of these regions is the termination shock, where the solar wind slows from supersonic to subsonic speeds. Voyager 1 crossed this boundary in December 2004, followed by Voyager 2 in 2007. The data from these crossings revealed that the termination shock is not a uniform structure. Instead, it fluctuates in response to changes in solar activity, such as variations in the intensity of the solar wind. Voyager's instruments recorded abrupt changes in particle density, magnetic field strength, and temperature as they passed through this turbulent zone. Beyond the termination shock lies the heliosheath, a region where the solar wind continues to slow and interact with the interstellar medium. In this zone, the flow of particles becomes chaotic, with turbulence and eddies forming as the solar wind loses its dominance. Voyager's sensors detected a mix of solar and interstellar particles, providing a unique glimpse into the boundary's complex dynamics. The heliosheath is a transitional region where the Sun's influence weakens but is not yet fully overcome by the forces of interstellar space. The outermost boundary of the heliosphere is the heliopause, where the pressure of the solar wind balances with the pressure of the interstellar medium. This is the true edge of the Sun's influence, beyond which lies interstellar space. Voyager 1 crossed the heliopause in August 2012, becoming the first human-made object to enter interstellar space. Voyager 2 followed in November 2018. Crossing the heliopause was a milestone in space exploration. For decades, scientists had debated the nature and location of this boundary. Voyager's data showed that the heliopause is not a sharp, well-defined edge, but a transition zone where solar particles give way to interstellar particles. The spacecraft detected a dramatic drop in the number of solar wind particles and a corresponding increase in cosmic rays, high-energy particles originating from outside the solar system. These observations confirmed that Voyager had entered a new realm, one dominated by the galaxy rather than the Sun. The heliosphere acts as a shield, deflecting many of the cosmic rays that would otherwise bombard the planets. By measuring the cosmic ray flux on either side of the heliopause, Voyager demonstrated how the heliosphere reduces the intensity of this radiation within the solar system. This shielding effect has implications for planetary habitability and the potential for life beyond Earth. It also highlights the challenges of interstellar travel, where spacecraft and future explorers would face much higher levels of radiation. The spacecraft also studied the magnetic fields that shape this boundary. The Sun's magnetic field, carried outward by the solar wind, forms a vast spiral structure that extends to the edges of the heliosphere. As Voyager crossed the heliopause, its instruments recorded a sudden change in the direction and strength of the magnetic field, providing direct evidence of the interstellar medium's magnetic influence. As the Voyagers continued their journey into interstellar space, they carried with them the legacy of their heliospheric discoveries. These spacecraft, designed for planetary exploration, had become pioneers of a new frontier, extending humanity's reach beyond the confines of the solar system. Their data not only defined the boundaries of the heliosphere, but also provided a foundation for future missions that will explore the interstellar medium in greater detail. The solar wind's final breath, the termination shock. The solar wind is one of the Sun's most far-reaching phenomena. It travels outward in all directions, carrying energy and magnetic fields across the solar system. Near the Sun, the wind moves at tremendous speeds, often exceeding 1,000,000 miles per hour. However, as it journeys outward, it spreads thinner and begins to encounter resistance from the interstellar medium. Crossing the termination shock was a moment of sudden change for the spacecraft. Voyager's instruments recorded sharp increases in particle density, temperature, and magnetic field strength. These changes provided the first direct evidence of the conditions at this distant boundary. Scientists had theorized about the termination shock for decades, but the Voyager's data transformed these theories into measurable realities. The observations showed that the solar wind did not simply stop at the termination shock. Instead, it slowed down and became turbulent, creating a chaotic environment where particles and magnetic fields swirled and interacted. Voyager's sensors detected a mix of low-energy particles from the solar wind and high-energy particles originating from the interstellar medium. These particles were accelerated to high speeds as they crossed the shock, a process that scientists had not fully understood before Voyager's mission. This particle acceleration provided insights into how cosmic rays are generated and how they propagate through space. The termination shock was not uniform. Voyager's data showed that it was a rippling, uneven surface shaped by fluctuations in the solar wind and the interstellar medium. This unevenness created regions of varying particle density and turbulence. The data also revealed differences in the termination shock structure between Voyager 1's crossing in the northern hemisphere of the heliosphere and Voyager 2's crossing in the southern hemisphere. These differences suggested that the Sun's magnetic field and the interstellar medium influence the shock in distinct ways depending on location. The turbulence of the termination shock was a significant challenge for Voyager's instruments. Despite being designed for planetary exploration, the spacecraft's sensors proved capable of adapting to the new environment. Instruments like the plasma detector and the magnetometer worked together to map the region's properties, providing a detailed picture of the conditions at the boundary. These measurements not only advanced our understanding of the solar system's outer layers, but also demonstrated the robustness of the Voyager's design. Voyager's instruments detected anomalous cosmic rays, which were distinct from the galactic cosmic rays that come from outside the solar system. Their presence suggested that the termination shock played a key role in shaping the particle environment at the heliosphere's edge. Voyager's data suggested that the heliosphere was not a perfect sphere, but rather an elongated structure influenced by the flow of the interstellar medium. The shock's location was farther from the Sun in some directions and closer in others, reflecting the pressure and movement of the surrounding space environment. For the scientists and engineers who had designed the Voyager mission, the termination shock was a major milestone. It marked the transition from the solar wind-dominated inner heliosphere to the turbulent and mixed environment of the heliosheath. The data from this region were invaluable for understanding the Sun's far-reaching effects and the processes that occur at the edge of its influence. The Voyager's ability to capture these measurements decades after their launch was a testament to the foresight and ingenuity of their creators. Mapping the heliosheath, the final frontier of the solar bubble. After the termination shock came the heliosheath. This vast, turbulent area between the termination shock and the heliopause is often described as the outermost layer of the solar bubble, a place where the Sun's influence wanes but still leaves its mark on the environment. The heliosheath is not a calm place. Here, the solar wind, now slowed to subsonic speeds, interacts with particles and magnetic fields from the interstellar medium. This interaction creates a chaotic environment where pressures, particle densities, and magnetic forces constantly shift. Voyager's instruments detected an increase in particle density compared to the region inside the termination shock. This rise was due to the piling up of solar wind particles that had slowed down but could not escape the Sun's influence entirely. The data revealed that this region was far more dynamic than previously imagined. Voyager recorded changes in the energy and density of particles, showing that the heliosheath was not uniform. These fluctuations were influenced by solar activity, such as coronal mass ejections and solar flares, which sent waves of energy through the solar wind. When these waves reached the heliosheath, they created disturbances that could be detected even billions of miles from the Sun. This connection between solar activity and the distant heliosheath underscored the far-reaching effects of the Sun's behavior. Voyager's magnetometer measured shifts in the strength and direction of the magnetic field, revealing a complex and tangled structure. This field was influenced by both the Sun's magnetic activity and the interstellar medium, creating a region of overlapping forces. Scientists had expected a smoother transition in the magnetic field as the spacecraft moved outward. But Voyager's data showed that the heliosheath was a far more intricate and active boundary. The interplay between the solar wind and the interstellar medium created a region of high turbulence, where particles were accelerated to unexpected speeds. These accelerated particles, including anomalous cosmic rays, were detected in higher concentrations than anticipated. This discovery suggested that the heliosheath played a significant role in shaping the particle environment at the edge of the solar bubble. It also raised new questions about how these particles might interact with the interstellar medium beyond the heliosphere. Voyager's data indicated that the heliosheath was not symmetrical. Instead, it appeared to be compressed on one side and extended on the other, influenced by the flow of the interstellar medium and the Sun's movement through space. This asymmetry was a reminder that the solar system is not isolated, but interacts with the larger galactic environment. The heliosheath's shape and size were shaped by these external forces, creating a boundary that was constantly in flux. The spacecraft detected a gradual rise in temperature as it moved outward, caused by the compression of solar wind particles and their interactions with the interstellar medium. However, this increase in temperature was accompanied by a drop in particle speed as the solar wind lost energy in the turbulent environment. These measurements provided a clearer picture of how energy is transferred and dissipated at the edge of the solar system. The spacecraft faced a constant bombardment of high-energy particles and fluctuating magnetic fields, yet its instruments continued to function with remarkable precision. This robustness allowed Voyager to gather data that would have been impossible to obtain through remote observations alone. As Voyager moved deeper into the heliosheath, it approached the heliopause. The data collected in the heliosheath provided critical context for understanding this ultimate transition. By mapping the turbulent region and measuring its properties, Voyager laid the groundwork for interpreting the changes that would occur as it crossed into interstellar space. Each measurement, each fluctuation in particle density or magnetic field strength, added to the story of the solar system's interaction with the galaxy beyond. A sudden silence. Voyager 1 exits the heliosphere. As Voyager 1 approached the outermost edge of the heliosheath, its instruments started to detect changes. The spacecraft had spent years moving through the turbulent region where the solar wind interacted with the interstellar medium, but the environment around it was becoming increasingly different. Measurements of solar wind particles were steadily decreasing, while galactic cosmic rays were becoming more frequent. These signs suggested that Voyager 1 was nearing the heliopause, the boundary where the Sun's influence truly ended. For decades, scientists had theorized about this boundary, but had no direct measurements to confirm its location or nature. Voyager 1 was about to provide that confirmation. On August 25, 2012, the spacecraft's instruments recorded a sudden and dramatic change. The solar wind particles that had been a constant presence since its launch all but disappeared. At the same time, the flux of galactic cosmic rays increased sharply. Voyager 1 had crossed the heliopause and entered interstellar space. The confirmation of this crossing came from multiple instruments working together. The spacecraft's plasma wave instrument played a key role. Although Voyager 1's primary plasma sensor had stopped working decades earlier, the plasma wave instrument was able to detect the density of charged particles around the spacecraft by measuring oscillations in the plasma. In interstellar space, these oscillations occur at a higher frequency due to the greater density of particles compared to the sparse solar wind inside the heliosphere. When Voyager 1 crossed the heliopause, the instrument recorded a clear and sustained increase in plasma density, confirming that it was no longer within the solar bubble. The transition was not immediate. Voyager 1 spent months in a transitional region where the solar wind and interstellar medium interacted more directly. Scientists referred to this area as a magnetic highway, where charged particles from the solar wind and cosmic rays could travel more freely along magnetic field lines. The crossing of the heliopause itself marked the end of this transitional zone and the beginning of a new chapter in Voyager 1's journey. One of the most striking aspects of the crossing was the near silence of solar particles. For the first time, Voyager 1 was in a region dominated by galactic influences rather than the Sun's. The spacecraft was still within the broader influence of the Milky Way's magnetic field, but it was now traveling through a medium shaped by supernovae, stellar winds, and other galactic phenomena. The increase in galactic cosmic rays was not just a confirmation of the crossing, it was also a glimpse into the environment beyond the heliosphere, a place shaped by forces far older and more powerful than the Sun. The data sent back by Voyager 1 after the crossing continued to surprise scientists. The interstellar medium was not the calm, uniform space many had envisioned. Instead, it was a dynamic and active region, with variations in particle density, temperature, and magnetic field strength. These variations provided clues about the processes occurring in the space between stars. Voyager 1's measurements showed that even here, far from any star, the universe was alive with motion and energy. For the first time, a human-made object had entered the space between stars, a region that had been the subject of speculation and imagination for centuries. Voyager 1's journey into interstellar space was a testament to the ingenuity and determination of the scientists and engineers who had designed the mission. It was also a reminder of the vastness of the universe and the small but significant steps humanity had taken to understand it. Even after crossing the heliopause, Voyager 1 continued to operate and send back data. Its instruments, though aging, remained functional, providing a continuous stream of information about the interstellar medium. Voyager 1's success inspired new questions about the boundaries of the solar system and the nature of interstellar space, questions that would guide the next generation of explorers. Voyager 2's unique journey, a comparative exit. Voyager 2 followed its sibling spacecraft on a path toward the edge of the solar system, but its journey unfolded in a way that provided a unique perspective. While Voyager 1 exited the heliosphere in 2012, Voyager 2's departure came 6 years later, in November 2018. This delay was not due to any malfunction, but because Voyager 2 took a different trajectory, allowing it to visit Uranus and Neptune before heading toward interstellar space. As a result, Voyager 2 exited the heliosphere at a different location and under different conditions, offering scientists a chance to compare and contrast the two journeys. Unlike Voyager 1, whose plasma instrument had failed decades earlier, Voyager 2 retained a working plasma sensor. This allowed it to provide direct measurements of the density, temperature, and speed of particles as it approached and crossed the heliopause. These measurements were critical for confirming the nature of the boundary and understanding how the solar wind interacts with the interstellar medium. While Voyager 1 had relied on indirect methods to estimate plasma density, Voyager 2's data offered a more complete picture. As Voyager 2 approached the heliopause, its instruments recorded a gradual decline in solar wind particles and a corresponding increase in galactic cosmic rays. The transition was less abrupt than Voyager 1's, suggesting that the boundary is not a uniform, sharp line, but rather a dynamic and variable region. This variability is influenced by the Sun's activity, which can cause the heliosphere to expand or contract over time. When Voyager 2 crossed the heliopause, its plasma instrument detected a sudden increase in particle density, confirming that it had entered interstellar space. This direct measurement matched the earlier findings from Voyager 1, providing additional evidence for the nature of the boundary. Voyager 2's crossing occurred in a different part of the heliosphere, giving scientists a chance to study how the Sun's influence varies with location. The heliosphere is not a perfect sphere, but an elongated bubble shaped by the movement of the solar system through the interstellar medium. Voyager 2 exited near the southern hemisphere of the heliosphere, while Voyager 1 had exited near the northern hemisphere. Comparing the data from these two crossings revealed subtle differences in the density and magnetic field strength of the interstellar medium, as well as variations in the solar wind's behavior near the boundary. The Sun goes through an 11-year cycle of activity, during which its magnetic field and solar wind output fluctuate. Voyager 1 exited the heliosphere during a period of relatively low solar activity, while Voyager 2 crossed during a more active phase. This difference influenced the structure of the heliopause and the nature of the transition region, with Voyager 2 encountering a more turbulent and compressed boundary. The complementary data from the two spacecraft provided a more complete understanding of the heliosphere's shape and behavior. Scientists used these observations to refine models of the heliosphere, including its interaction with the interstellar medium. The data also offered insights into the processes that govern the boundary region, such as magnetic reconnection, where magnetic field lines from the Sun and the interstellar medium interact and exchange energy. These processes are not unique to the heliosphere, but occur throughout the universe, making Voyager's findings relevant to a wide range of astrophysical phenomena. While the interstellar space beyond the heliopause was expected to be relatively uniform, Voyager 2's instruments detected fluctuations in particle density and magnetic field strength. These variations suggested that the interstellar medium is shaped by events such as supernovae and stellar winds, which create pockets of higher or lower density. By comparing the observations from Voyager 1 and Voyager 2, scientists were able to map these variations and gain a better understanding of the local interstellar environment. The dual perspectives of Voyager 1 and Voyager 2 also provided valuable information about the heliosheath. Voyager 2's working plasma instrument allowed it to measure the properties of this region in greater detail, revealing the presence of turbulence and complex flows of particles. These findings complemented Voyager 1's earlier observations and helped to build a more complete picture of the processes occurring at the edge of the solar system. The spacecraft's unique trajectory and working instruments allowed it to provide data that Voyager 1 could not, filling in gaps and answering questions that had arisen from the earlier mission. Together, the two Voyagers painted a detailed and dynamic picture of the heliosphere and its interaction with the interstellar medium, transforming our understanding of the Sun's influence and the environment beyond. The interstellar wind, a new cosmic breeze. As the Voyager spacecraft ventured into interstellar space, they encountered an entirely new kind of environment, one shaped by the interstellar wind. Unlike the solar wind, which originates from the Sun and dominates the heliosphere, the interstellar wind flows through the galaxy, carrying the imprints of distant stars and cosmic events. This wind is made up of particles and magnetic fields that drift between the stars, shaped by the life cycles of those stars and the gravitational dynamics of the Milky Way. Observations from Earth-based instruments and earlier space missions had hinted at its presence, but Voyager's crossing of the heliopause offered a chance to measure it directly. The spacecraft's instruments detected subtle changes in particle densities, magnetic fields, and directional flows as they moved farther from the Sun's influence. These changes were evidence of the transition from the heliosphere's solar-dominated environment to the vast, uncharted territory of interstellar space. The interstellar wind moves at speeds of around 26 kilometers per second relative to the Sun. Its direction is not random, but influenced by the Sun's motion through the galaxy. As the solar system travels, it creates a sort of bow wave, much like a boat moving through water. Voyager's observations confirmed that the heliosphere acts as a protective shield against this wind, deflecting and slowing down the particles that attempt to enter. Beyond the heliopause, the interstellar wind becomes the dominant force, its particles and fields interacting with the remnants of the solar wind in a complex dance. Variations in particle density and magnetic field strength revealed that the interstellar medium is shaped by distant astrophysical events. Supernovae, for instance, release shock waves that ripple through the galaxy, compressing and heating the surrounding material. These events leave behind regions of higher particle density and altered magnetic fields, which Voyager's instruments were able to detect. The spacecraft essentially became interstellar weather stations, measuring the cosmic winds and magnetic currents that flow between the stars. The interstellar wind also carries chemical signatures that tell a story of its origins. Elements like hydrogen, helium, and heavier atoms such as oxygen and nitrogen are present in the wind, each one tracing back to the processes that created them. Some of these elements were forged in the hearts of stars, while others were scattered into space during supernova explosions. By analyzing the composition of the interstellar wind, scientists gained insights into the history of star formation and the recycling of matter in the galaxy. Voyager's measurements also provided clues about the direction of the interstellar wind. The data showed that the wind's flow is not aligned with the Sun's motion through the galaxy, but slightly tilted. This misalignment suggests that the interstellar medium itself is shaped by large-scale magnetic fields and currents within the galaxy. These fields can bend and twist the flow of particles, creating patterns that Voyager's instruments were able to detect. By mapping these patterns, scientists began to understand the larger forces at play in the Milky Way. One interesting aspect of the interstellar wind is its relationship with cosmic rays. These high-energy particles, which originate from sources like supernovae and black holes, travel through the galaxy and interact with the interstellar wind. Voyager's instruments detected variations in cosmic ray intensities as they moved farther from the heliosphere, revealing how the interstellar wind affects the distribution of these particles. The data showed that the interstellar wind acts as a sort of filter, allowing some cosmic rays to pass through while deflecting others. As humanity plans for interstellar probes and explores the possibility of sending spacecraft to other star systems, the data collected by Voyager becomes invaluable. The interstellar wind represents one of the many challenges that such missions will face, from its effects on spacecraft navigation to its potential impact on communication systems. Voyager's journey into the interstellar wind was a pioneering step, offering a glimpse of what lies beyond the protective bubble of the heliosphere. While the Sun's influence dominates the solar system, it is only a small player in the larger galactic environment. Voyager's data reminds us that the Sun is part of a dynamic, interconnected system of stars, magnetic fields, and particles. Galactic radiation, a window into interstellar space. As Voyager moved into interstellar space, it entered a region dominated by galactic radiation, primarily in the form of cosmic rays. These rays offered a new way to study the broader environment beyond the Sun's influence. Unlike the solar wind, which diminishes at the heliopause, cosmic rays are omnipresent in interstellar space, streaming from all directions. They are composed mainly of protons, with smaller numbers of helium nuclei and electrons, and trace amounts of heavier elements. Their origins are diverse, with many of them accelerated to high energies by events like supernova explosions. As these stellar remnants collapse and release immense amounts of energy, they create shock waves that propel particles to near-light speeds. Some cosmic rays originate from more exotic sources, like pulsars, black holes, or even the turbulent environments of galaxy clusters. By studying cosmic rays, scientists can learn about these distant phenomena, even when the objects themselves are too far to observe directly. Before crossing the heliopause, Voyager detected cosmic rays that had been modulated by the heliosphere. The Sun's magnetic field and solar wind act as a shield, deflecting and slowing down many cosmic rays, particularly those with lower energies. This shielding effect is strongest near the Sun and diminishes with distance. When Voyager entered interstellar space, it was exposed to cosmic rays in their unaltered form for the first time. One of the most important aspects of Voyager's observations was the ability to measure the composition and energy spectrum of cosmic rays in interstellar space. The data revealed that high-energy cosmic rays are more abundant beyond the heliosphere, while lower-energy rays are largely blocked by the solar wind. Cosmic rays are not just particles. They carry magnetic fields and interact with the magnetic environment of the galaxy. Voyager's instruments detected subtle variations in the magnetic field, strength and direction as cosmic rays passed through. These variations helped scientists map the magnetic field lines that thread through interstellar space. The data showed that these fields are not uniform, but are shaped by turbulent processes, likely driven by the movements of stars and the explosions of supernovae. When cosmic rays collide with interstellar atoms, they produce secondary particles and isotopes, some of which are rare or unstable. These secondary particles serve as markers, allowing scientists to trace the origins and histories of cosmic rays. For example, the detection of certain isotopes can indicate how long cosmic rays have been traveling through space, and whether they passed through regions of dense interstellar gas. These high-energy particles can penetrate spacecraft and ionize biological tissue, posing risks for future crewed missions beyond the heliosphere. Voyager provided crucial data for assessing the radiation environment that astronauts might face on interstellar journeys, underscoring the need for advanced shielding technologies and other protective measures for deep space exploration. When cosmic rays interact with interstellar gas, they ionize atoms and molecules, influencing the chemistry and dynamics of these clouds. Ionized gas is more susceptible to magnetic fields, which can affect the collapse of clouds into stars. By studying cosmic rays, scientists can better understand the conditions that lead to star formation and the processes that govern the evolution of the galaxy. The data also showed that the heliosphere is not a perfect shield. Some cosmic rays manage to penetrate even the innermost regions of the solar system. This leakage provides a way to study how cosmic rays interact with the heliosphere's magnetic fields and how the heliosphere changes over time. These particles travel vast distances, crossing regions with widely varying conditions. Their journeys are shaped by the gravitational pull of stars, the magnetic fields of interstellar clouds, and the turbulence of galactic winds. By the time they reach Voyager, cosmic rays have traveled through a rich tapestry of environments, carrying information about the galaxy's history and structure. Each particle is like a tiny messenger, offering a glimpse of the processes that govern the Milky Way. A song of plasma waves, the music of the cosmos. Among the instruments Voyager carried into the depths of interstellar space was the plasma wave subsystem, a tool capable of measuring the subtle oscillations in charged particles that make up plasma, the most abundant state of matter in the universe. Plasma waves, though imperceptible to the human ear in their raw form, could be converted into sound, revealing music that captured the essence of the cosmos. Plasma is a collection of free electrons and ions, moving chaotically but governed by electromagnetic forces. These particles vibrate in waves, creating disturbances that ripple through space. The frequency and intensity of these waves depend on the density and temperature of the plasma. By measuring these vibrations, Voyager provided insights into the environment it traversed, painting a picture of space not as a silent void, but as a dynamic, ever-changing medium. The first notable plasma wave data came when Voyager 1 crossed the heliopause and entered interstellar space. At this boundary, the solar wind slowed and collided with the interstellar medium, creating a turbulent region of compressed plasma. The instruments aboard Voyager detected this turbulence, capturing bursts of plasma waves that marked the spacecraft's transition into a new realm. The pitch and intensity of these waves reflected the density of the plasma, which was significantly higher in interstellar space than within the heliosphere. When these plasma waves were converted into sound, they revealed a series of eerie, oscillating tones. These sounds, sometimes described as whistles or hums, resonated with an almost otherworldly quality. Scientists likened them to a symphony of the cosmos, a natural expression of the forces at play in the universe. Each burst of sound represented a specific interaction, whether it was the movement of charged particles, the compression of plasma, or the influence of magnetic fields. The recordings offered a new way to experience space, translating invisible phenomena into something tangible and relatable. Voyager's measurements indicated that the plasma density outside the heliosphere was about 40 times higher than within it. This finding confirmed that interstellar space is filled with a diffuse soup of particles left over from ancient stars and other cosmic events. These particles form the interstellar medium, a vital component of the galaxy's structure and evolution. By studying the plasma waves in this medium, Voyager helped scientists understand its properties and dynamics. One of the most striking plasma wave recordings came in the form of a gradual rise in frequency over several months. This rise corresponded to Voyager 1's movement through a region of increasing plasma density, suggesting that the spacecraft was encountering a denser pocket of interstellar material. As Voyager moved farther from the Sun, it continued to detect occasional bursts of plasma waves, likely caused by solar events such as coronal mass ejections. These bursts traveled outward, compressing the interstellar plasma and creating distinct wave patterns. By analyzing these interactions, scientists gained a deeper understanding of how the Sun's influence extends beyond the heliosphere, reaching into interstellar space. The recordings of plasma waves have not only scientific value, but also cultural and philosophical significance. They remind us that space, often perceived as silent and empty, is alive with activity. The sounds captured by Voyager are a testament to the dynamic nature of the universe, where even the most remote regions are shaped by waves of energy and matter. These recordings have been shared with the public and have been used in music, art, and education, serving as a bridge between science and human creativity. Magnetic mysteries, the unexpected alignment. In the interstellar medium, Voyager's magnetometer recorded something unexpected, a curious alignment in the magnetic fields it encountered. Scientists had anticipated a chaotic, tangled environment where magnetic fields pointed in seemingly random directions, shaped by eons of turbulent interactions between interstellar winds, cosmic radiation, and the remnants of ancient supernovae. Instead, Voyager's data hinted at a surprising order. The interstellar magnetic fields appeared to show a degree of alignment, particularly near the boundary where the heliosphere transitions into the interstellar medium. Magnetic fields in space are generated by the movement of charged particles, often through processes tied to stars, galaxies, and the broader dynamics of the universe. In theory, these fields should be influenced by countless local factors, creating a patchwork of directions and intensities. But the alignment detected by Voyager suggested that there might be larger-scale forces at work, imposing a structure on the interstellar medium that extends far beyond the influence of any single star or event. The alignment seemed to correspond with the orientation of the Sun's magnetic field near the heliopause. As the solar wind pushes outward, it carries the Sun's magnetic field with it, forming a bubble around the solar system. Voyager's observations showed that the interstellar magnetic field just outside this bubble wasn't oriented at random, but instead seemed to align, at least partially, with the boundary of the heliosphere. One possibility is that the alignment is a result of the Sun's motion through the interstellar medium. Like a boat moving through water, the solar system creates a kind of bow shock as it travels through space. This interaction could compress and shape the interstellar magnetic field, forcing it into a configuration that mirrors the contours of the heliosphere. Another explanation for the alignment could lie in the large-scale structure of the galaxy's magnetic field. The Milky Way is thought to have a weak but coherent magnetic field, generated by the motion of charged particles within its disk. This galactic magnetic field is not uniform. It varies in strength and direction depending on the local environment. Voyager's observations suggest that the interstellar magnetic field near the Sun might be influenced by these larger galactic currents, aligning with the dominant direction of the Milky Way's magnetic field lines. If the alignment is a result of galactic-scale forces, it could provide valuable clues about the structure and behavior of magnetic fields across the Milky Way. Magnetic fields are notoriously difficult to study because they are invisible and interact with matter in complex ways. Voyager's measurements offer a rare opportunity to probe these fields directly, providing data that can be used to test and refine models of galactic magnetism. The alignment of the interstellar magnetic field near the heliosphere could help explain how cosmic rays interact with the Sun's magnetic bubble. By guiding these particles, the interstellar magnetic field may play a role in determining the intensity and composition of cosmic rays that reach the solar system. Magnetic fields are thought to be amplified and sustained by a process known as the dynamo effect, which occurs when conducting fluids or plasmas move within a rotating system. In the case of the galaxy, this process might be driven by the motion of gas and dust in the Milky Way's disk. The alignment detected by Voyager could provide indirect evidence of this mechanism, offering clues about how magnetic fields are generated and maintained on a cosmic scale. The alignment has practical implications for our understanding of space weather. As the Sun moves through the interstellar medium, it encounters variations in the density and direction of magnetic fields. These variations can affect the shape and behavior of the heliosphere, which in turn influences the flow of cosmic radiation into the solar system. By studying the alignment and its causes, scientists can improve models of space weather and its potential impacts on Earth. Magnetic fields can influence the motion of particles, guiding them along field lines and creating structures within the medium. They can also affect the formation of stars and planets, as magnetic forces can compress or inhibit the collapse of gas clouds. The alignment detected by Voyager suggests that magnetic fields play a more significant role in the interstellar medium than previously thought, shaping its structure and dynamics on both local and galactic scales. Interstellar dust, tiny clues to the galaxy's history. Interstellar dust is a critical component of the galactic ecosystem, influencing everything from star formation to the chemical evolution of planets. Scientists had long theorized about the existence of these particles, which are formed through processes like supernova explosions, stellar winds, and the cooling of gas in molecular clouds. What was surprising, however, was the richness of the data Voyager was able to collect. By measuring the size, velocity, and composition of these particles, the spacecraft provided insights that had previously been beyond the reach of even the most advanced telescopes. Interstellar dust is composed of a mix of elements and compounds, including silicates, carbon, and ice. These particles are often less than a micron in size, smaller than the width of a human hair. Despite their small size, they play an outsized role in shaping the interstellar medium. Dust grains can absorb and scatter light, creating the dark patches and glowing regions observed in nebulae. They also serve as the building blocks for larger structures, such as planets and comets, forming the seeds around which material can accumulate. By analyzing the particles it encountered, the spacecraft revealed differences in the abundance of elements like carbon, silicon, and iron. These variations reflect the diverse origins of the dust, which can trace its lineage back to different types of stars and cosmic events. For example, some grains may have formed in the outer layers of red giant stars, while others could be the remnants of supernova explosions. Dust grains can travel vast distances, carried by the winds of stellar outflows or the shock waves of supernovae. Along the way, they interact with gas and other particles, contributing to the chemical evolution of the regions they pass through. This process is essential for the formation of new stars and planets, as it delivers the raw materials needed to create complex structures and, ultimately, life itself. Dust grains can act as tiny shelters, protecting fragile molecules from the intense radiation and high-energy particles that permeate the galaxy. This protective effect allows complex molecules, including those that could be precursors to life, to survive and potentially be transported to new regions. Voyager's data provided evidence of this process, showing how dust grains contribute to the stability and longevity of molecular structures in space. Dust grains are often charged, meaning they can be influenced by the magnetic fields that thread through the galaxy. This interaction can align the grains, causing them to emit polarized light. By studying this polarization, scientists can map the structure of magnetic fields and gain insights into their role in shaping the interstellar medium. As Voyager approached and eventually crossed the heliopause, it encountered a change in the density and composition of dust particles. The dust particles Voyager detected in this region were smaller and more uniform than those within the heliosphere, suggesting that the heliopause acts as a filter, allowing only certain types of particles to pass through. Far from being static, the dust is constantly shaped and reshaped by the forces of the galaxy. Shockwaves from supernovae can compress and fragment dust clouds, while radiation from stars can heat and evaporate them. These processes create a constantly evolving landscape, with dust grains forming, breaking apart, and reforming over time. Dust grains are the building blocks of protoplanetary disks, the swirling clouds of material that give rise to planets and other celestial bodies. The composition and distribution of dust in these disks can influence the types of planets that form, as well as their potential for hosting life. Voyager's observations provided a baseline for comparing interstellar dust with the material found in protoplanetary disks, helping to bridge the gap between the study of the galaxy and the study of planetary systems. Dust particles can also pose a hazard to spacecraft, as their high speeds can cause significant damage upon impact. By studying the properties of interstellar dust, scientists can better understand the risks associated with deep space missions and develop strategies for protecting spacecraft. Voyager's fading signal, communicating across vast distances. The faint whisper of Voyager's signal, traveling across billions of kilometers of space, is one of humanity's most remarkable achievements. From the moment the spacecrafts were launched in 1977, maintaining contact with them has been a priority. Yet the challenges of communicating with these distant emissaries grow as they journey farther from Earth. Each spacecraft is equipped with a high-gain antenna, a 3.7-meter wide dish that transmits and receives radio waves. These signals are incredibly weak by the time they reach Earth, diminishing in strength as the spacecraft moves farther away. For perspective, the power of Voyager's transmitter is roughly 20 watts, about the same as a refrigerator light bulb. By the time this signal reaches Earth, it is billions of times weaker than the background noise of space. Detecting such a faint signal requires extraordinary precision and advanced technology. The Deep Space Network, or DSN, is the backbone of communication with Voyager. Operated by NASA, the DSN consists of 3 complexes located in California, Spain, and Australia. This global configuration ensures continuous contact with spacecraft as the Earth rotates. Each complex is equipped with massive antennas, some as large as 70 meters in diameter. These antennas are designed to capture Voyager's faint signals and relay them to mission control. Over the decades, the DSN has been upgraded to improve its sensitivity, allowing it to detect signals from distances that were once unimaginable. Even with these advanced systems, the delay in communication is significant. Voyager 1, the farthest human-made object, is around 25 billion kilometers from Earth. At this distance, it takes nearly 24 hours for a signal to travel one way. This delay means that real-time control of the spacecraft is impossible. Instead, commands are carefully planned and uploaded well in advance. The spacecraft then execute these commands autonomously, with their onboard systems making adjustments as needed. Each spacecraft carries instruments that measure particles, magnetic fields, and other phenomena. The data collected is stored in an onboard computer and transmitted to Earth in carefully compressed packets. Given the limited bandwidth and the vast distance, only a small amount of data can be sent at a time. Engineers must prioritize which observations to transmit, ensuring that the most valuable information reaches Earth. As Voyager moves farther away, the signal weakens, and the challenge of decoding it becomes even greater. The signal-to-noise ratio is a critical factor. Engineers use sophisticated algorithms to filter out background noise and extract the data encoded in the radio waves. These techniques have been refined over decades, allowing scientists to continue receiving useful information from the spacecraft despite the increasing distance. The spacecraft were designed for a mission lasting only a few years, yet their transmitters and antennas have operated reliably for more than 4 decades. This durability is a testament to the meticulous engineering and rigorous testing that went into their design. But the aging hardware presents many challenges. Components degrade over time, and maintaining contact with the spacecraft requires constant monitoring and occasional adjustments to account for these changes. Voyager relies on RTGs for power. These devices convert heat from the natural decay of plutonium-238 into electricity. Over time, the plutonium decays and the power output gradually decreases. To conserve energy, engineers have turned off non-essential systems and instruments, focusing on keeping the communication system and key scientific instruments operational. Despite these measures, the power supply will eventually be insufficient to support even basic functions. The diminishing power and increasing distance have spurred innovation in how data is handled. Engineers have developed techniques to enhance the efficiency of both the spacecraft's transmitters and the DSN's receivers. One approach involves using new methods of signal processing to improve the ability to detect and decode Voyager's transmissions. Another involves carefully managing the spacecraft's remaining energy to ensure that it can continue to send data for as long as possible. The vast distances involved push the boundaries of what is possible with radio communication. These challenges have inspired new approaches to deep space communication, including the potential use of lasers for future missions. Laser communication systems promise higher data rates and greater efficiency, offering a glimpse of what might be possible in the next generation of space exploration. The faint signal represents a connection to a distant part of the universe, a link to a mission that has expanded our understanding of the cosmos. Each bit of data received is a testament to the ingenuity and perseverance of the people who have kept the spacecraft operational for so long. Powering the journey, the plutonium-238 lifeline. The longevity of the Voyager spacecrafts owes much to the devices powering them. These nuclear batteries, or RTGs, have provided a steady supply of electricity for more than 4 decades, enabling the spacecraft to operate their instruments, communicate with Earth, and continue their journey into the depths of interstellar space. Without the RTGs, the Voyager missions would have ended long ago, leaving much of their groundbreaking exploration unfinished. RTGs work by converting heat from the natural radioactive decay of plutonium-238 into electricity. This process relies on thermoelectric materials, which generate a voltage when exposed to a temperature difference. The system has no moving parts, making it incredibly reliable and ideal for the harsh conditions of deep space. Plutonium-238 was chosen for its unique properties. It has a half-life of 87.7 years, meaning it remains active for a long time, and its decay produces a significant amount of heat. Unlike nuclear reactors, which require complex mechanisms to sustain a chain reaction, RTGs rely on the steady, predictable decay of radioactive material. This simplicity makes RTGs highly dependable, even in extreme environments where maintenance or repair is impossible. The Voyager spacecraft each carry 3 RTGs, mounted on a boom that extends away from the main body of the spacecraft. This placement helps to keep the heat generated by the RTGs from interfering with the sensitive instruments on board. Each RTG contains about 4.5 kilograms of plutonium-238 dioxide, encased in a protective shell to prevent the release of radioactive material in the event of an accident during launch. The design was carefully tested to ensure it could withstand the stresses of the launch and the vacuum of space. At the time of launch, the RTGs on each Voyager spacecraft produced approximately 470 watts of electrical power. This was more than sufficient to power the instruments, communication systems, and other onboard equipment. However, as the plutonium-238 decays, the amount of heat it produces decreases, and with it, the amount of electricity generated by the RTGs. This gradual decline in power output has required careful management of the spacecraft's energy resources over the years. The engineers and scientists managing the Voyager missions have had to make difficult decisions about which systems and instruments to prioritize as the power supply dwindles. Some instruments have been turned off to conserve energy, while others have been reconfigured to operate on reduced power. The RTGs also provide heat to keep the spacecraft systems from freezing in the frigid temperatures of deep space. This thermal energy is distributed through the spacecraft using a combination of insulation and heat pipes, ensuring that critical components remain within their operational temperature ranges. Without this additional heat, the extreme cold of space could render the spacecraft inoperable. The use of RTGs on Voyager was not without controversy. The launch of the spacecraft in 1977 sparked concerns about the safety of carrying radioactive material into space. Critics worried about the potential consequences of a launch failure or an accident that could release plutonium-238 into the environment. NASA and its partners addressed these concerns through rigorous testing and safety measures, including the development of a robust containment system for the plutonium-238. These precautions ensured that the risk to public safety was minimal, and the successful launches of Voyager 1 and 2 demonstrated the effectiveness of these measures. RTGs have been used on other space missions as well, including the Pioneer, Galileo, and Cassini spacecraft, as well as the Mars rovers, Curiosity and Perseverance. Each of these missions has benefited from the reliability and durability of RTGs, which provide a consistent power source in environments where solar power is impractical or insufficient. The success of these missions underscores the importance of RTGs as a tool for space exploration. The supply of plutonium-238 has been a concern for space agencies in recent years. The production of this isotope requires specialized facilities and expertise, and for a time, the global supply was limited. Efforts to restart production in the United States have been successful, ensuring that future missions can continue to use RTGs. However, the scarcity of plutonium-238 highlights the challenges of relying on this resource for deep space exploration. From their close encounters with the outer planets to their journey into interstellar space, the Voyagers have expanded our understanding of the universe and our place within it. The data they have collected would not have been possible without the steady, reliable power provided by their RTGs. Eventually, the RTGs will reach a point where they can no longer generate enough power to sustain the spacecraft's systems. This moment will mark the end of an era, but the legacy of the Voyagers will endure. Lessons from Voyager for future interstellar missions. The Voyager missions were not only a triumph of their time, but also a guiding light for the future of interstellar exploration. The lessons learned from these spacecraft have profoundly shaped how scientists and engineers think about sending probes into the vast expanse of space. From their robust design to the wealth of data they continue to provide, the Voyagers have laid the foundation for what future missions must consider when venturing far beyond our solar system. The spacecraft were built to last far longer than their original mission timeline, which focused on exploring the outer planets. Their robust construction and redundant systems allowed them to continue functioning for decades as they pushed into interstellar space. This durability was not accidental. Engineers designed Voyager with a clear understanding that it would face conditions unlike any encountered before, including intense radiation, temperature extremes, and the vacuum of space. Future interstellar missions will need to embrace this principle of resilience, ensuring that probes can survive the unknown for extended periods. Voyager's RTGs have been a critical factor in the mission's longevity, providing a steady energy supply regardless of distance from the Sun, which would be a limiting factor if the probes were powered solely by solar panels. This has allowed Voyager to continue transmitting data long after solar panels would have become ineffective. For future missions aiming to travel even farther, RTGs or similar technologies will be essential. There is growing interest in exploring advanced propulsion and energy systems that could offer even greater efficiency and longevity. One challenge highlighted by Voyager's experience is the need for efficient communication systems. Maintaining contact with spacecraft billions of kilometers away requires a delicate balance of signal strength, antenna design, and ground-based infrastructure. The Deep Space Network demonstrates the importance of investing in Earth-based support systems. Future interstellar missions will likely need more advanced communication technologies, such as laser-based systems, to handle the increased distances and data requirements. The data Voyager collected during its encounters with the outer planets revealed the value of multi-purpose instruments. Each spacecraft carried a suite of scientific tools designed to study various aspects of its surroundings, from magnetic fields to particle density. These instruments were not only versatile, but also capable of adapting to new objectives as the mission evolved. For future missions, designing flexible instruments that can provide meaningful data in a variety of conditions will be essential. This adaptability ensures that even unexpected discoveries can be thoroughly investigated. The spacecraft took advantage of a rare planetary alignment to perform a gravity assist maneuver, gaining speed and altering their course with the help of the outer planets. This clever use of celestial mechanics allowed them to reach interstellar space much faster than they would have otherwise. Future missions will need to consider similar strategies, perhaps using the gravitational pull of stars or other objects to propel them deeper into space. Planning these trajectories with precision can save time, energy, and resources. Voyager's distance from Earth means that signals take hours to travel between the spacecraft and mission control. This delay makes real-time decision-making impossible, requiring the spacecraft to operate independently to a significant degree. While Voyager's autonomy was limited by the technology of the 1970s, it set a precedent for future missions. Advanced artificial intelligence and machine learning could enable new probes to analyze data, make decisions, and adapt to unforeseen circumstances without waiting for instructions from Earth. The Voyager missions also emphasized the importance of understanding and mitigating risks. For instance, the spacecraft had to navigate through intense radiation belts around Jupiter and avoid potential collisions with micrometeoroids. These experiences have underscored the need for robust shielding and risk assessment in mission planning. Future interstellar missions will face even greater uncertainties, requiring innovative approaches to safeguard the spacecraft and its instruments. Voyager's journey through the heliosphere and into interstellar space has provided invaluable insights into the boundaries of our solar system. This knowledge is shaping how scientists think about the next generation of missions. Understanding the heliosphere's structure, the termination shock, and the interstellar medium helps engineers design instruments capable of capturing data in these unique environments. For example, future missions might include more sensitive detectors to measure the properties of interstellar particles, or advanced magnetometers to map cosmic magnetic fields in greater detail. The mission involved scientists and engineers from around the world, and its discoveries have benefited all of humanity. As space exploration becomes increasingly ambitious, pooling resources, expertise, and funding from multiple nations will be critical. Collaborative efforts can help overcome the immense challenges of interstellar travel, from developing new technologies to addressing ethical considerations. Originally intended as a planetary exploration mission, Voyager's success in reaching interstellar space was a testament to the power of curiosity and determination. Future missions will build on this legacy, pushing the boundaries of what is possible and continuing the journey into the unknown. Voyager and the search for extraterrestrial life. The Voyager spacecraft, while not explicitly designed to search for life, have provided valuable insights into the conditions and environments that might support it. Their journey through the solar system and beyond has yielded data that helps scientists refine the criteria for habitability and narrow down the search for extraterrestrial life. By studying the planets, moons, and the space between the stars, Voyager has offered clues about where life might arise and how it could endure in extreme conditions. One of Voyager's most significant contributions to the search for life came from its exploration of the outer planets and their moons. As Voyager 1 and 2 flew past Jupiter, they captured stunning images and data about its largest moons. Among them, Europa stood out. Voyager's observations revealed a smooth, icy surface, crisscrossed by dark streaks, suggesting the possibility of an ocean beneath. Although Voyager lacked the instruments to directly detect liquid water, its findings paved the way for later missions, such as Galileo and Europa Clipper, which continue to investigate this intriguing moon. The presence of water, a key ingredient for life as we know it, makes Europa a prime candidate in the search for extraterrestrial organisms. Saturn's system also yielded surprises. Voyager's flybys revealed details about Titan, Saturn's largest moon, including its dense, nitrogen-rich atmosphere. The spacecraft detected complex organic molecules in Titan's haze, raising questions about the chemistry occurring on its surface. Later missions confirmed that Titan has lakes and seas of liquid methane and ethane, environments vastly different from Earth, but still capable of supporting unique forms of life. Voyager's observations were the first step in uncovering Titan's potential as a laboratory for studying prebiotic chemistry and the limits of habitability. The search for life isn't limited to moons. Voyager's study of the gas giants themselves offered insights into the atmospheres of planets like Jupiter and Saturn. While these worlds are unlikely to host life due to their lack of a solid surface and extreme conditions, the data gathered helps scientists understand how atmospheres evolve and interact with their environments. Such knowledge is crucial for assessing the habitability of exoplanets orbiting distant stars. By comparing the atmospheres of gas giants in our solar system, researchers can identify signatures that might indicate the presence of life on similar planets elsewhere. Voyager's exploration of Uranus and Neptune, while less directly linked to the search for life, also contributed to the broader understanding of planetary systems. The spacecraft revealed dynamic atmospheres, magnetic fields, and unusual moon systems that challenge our assumptions about where life could exist. For example, Triton, Neptune's largest moon, has geysers of nitrogen gas erupting from its surface, hinting at subsurface activity. Such geological processes could create pockets of liquid water beneath Triton's icy crust, offering another potential habitat for life. As the spacecraft crossed the heliopause and entered interstellar space, they measured the density and composition of particles in this vast, uncharted region. Understanding the interstellar medium is critical for evaluating the potential for life beyond our solar system. It serves as the backdrop against which stars and planets form, influencing the availability of key elements like carbon, hydrogen, oxygen, and nitrogen. Voyager's data helps scientists piece together the chemical landscape of our galaxy, shedding light on the building blocks available for life in different regions. In our solar system, the Sun provides the primary energy that sustains life on Earth. However, Voyager's observations of moons like Europa and Enceladus suggest that other energy sources, such as tidal heating, could also play a role. Tidal forces generated by the gravitational pull of a planet can create internal friction and heat within a moon, potentially sustaining subsurface oceans or driving hydrothermal activity. These processes could provide the necessary conditions for life to thrive, even in the absence of sunlight. The spacecraft's findings underscore the diversity of environments where life might exist. By revealing the unexpected activity on moons, the complex chemistry of atmospheres, and the dynamic interactions between celestial bodies, Voyager expands the range of possibilities for habitability. It challenges the traditional notion that life requires Earth-like conditions, opening the door to exploring more extreme and unconventional environments. In addition to gathering data, Voyager carries a symbolic message about the search for life. The golden records, affixed to each spacecraft, serve as time capsules containing sounds, images, and greetings from Earth. These records are a testament to humanity's desire to connect with other civilizations, should they exist. While the likelihood of the records being discovered by extraterrestrial beings is remote, they reflect the optimism and curiosity driving the search for life beyond our planet. The lessons learned from its journey inform the design of new spacecraft and instruments, ensuring that they are equipped to probe the most promising environments. For example, missions like Europa Clipper and Dragonfly build on Voyager's discoveries, targeting moons and planets that show signs of habitability. These missions are equipped with advanced technology capable of analyzing surface compositions, detecting subsurface oceans, and even searching for biosignatures. By studying the atmospheres and surfaces of worlds within our solar system, scientists can identify the markers of habitability and develop techniques to detect them from afar. This knowledge is applied to missions like the James Webb Space Telescope, which seeks to identify potentially habitable exoplanets by analyzing their light spectra for signs of water, oxygen, and other life-related compounds. A glimpse of the Oort cloud, the solar system's farthest frontier. The Oort cloud, a vast and distant shell of icy bodies surrounding the solar system, represents the farthest frontier of our Sun's influence. While Voyager 1 and Voyager 2 have not reached the Oort cloud and will not do so for tens of thousands of years, their journey offers indirect insights into this enigmatic region. The Oort cloud is thought to be a reservoir of comets, remnants from the early formation of the solar system. It exists in a distant spherical shell, stretching from roughly 2,000 to 100,000 astronomical units from the Sun. This vast distance places it far beyond the planets, the Kuiper belt, and even the heliopause, where Voyager probes have ventured. Though Voyager cannot directly detect objects in the Oort cloud, the data it has collected about the solar wind and interstellar medium provides valuable context for understanding this mysterious region. The spacecraft's passage through the heliosphere and into interstellar space has allowed scientists to define the boundaries of the solar system more precisely. The Oort cloud exists at the outermost edge of this influence, where the Sun's gravity still holds sway, but its other forces, such as the solar wind, have faded. By identifying the point at which the solar wind gives way to the interstellar medium, Voyager provides a clearer picture of the environment surrounding the Oort cloud. The density and composition of interstellar particles detected by Voyager give clues about the environment that the Oort cloud's icy bodies inhabit. These particles interact with the Sun's gravity and the faint remnants of the solar wind that may still influence the inner regions of the Oort cloud. By studying these interactions, researchers can better understand how the Oort cloud's objects remain in their distant orbits, and how they might be perturbed by passing stars or interstellar forces. The Oort cloud is believed to have formed during the early days of the solar system, as icy bodies were scattered outward by the gravitational forces of the giant planets. Voyager's data about the outer planets and their gravitational influence contribute to models of how these scattering processes occurred. One of the intriguing aspects of the Oort cloud is its role as a source of long-period comets, which occasionally enter the inner solar system. These comets provide a glimpse into the materials that existed during the solar system's formation. Voyager's data about the heliosphere and interstellar space inform our understanding of the paths these comets take. When a comet from the Oort cloud begins its journey toward the Sun, it must pass through the outer reaches of the solar system, encountering the regions Voyager has explored. The spacecraft's measurements of particle density, magnetic fields, and cosmic rays help scientists model the conditions these comets experience on their journey. The Oort cloud exists at the boundary between the solar system and the interstellar environment, where the Sun's influence meets the broader forces of the Milky Way. Voyager's data about interstellar magnetic fields and cosmic ray flux reveal the forces acting on the Oort cloud's objects. These forces can cause gradual changes in the orbits of Oort cloud bodies, occasionally sending them hurtling toward the inner solar system. Understanding these processes is crucial for studying the origins of long-period comets and their potential impacts on Earth. Although direct exploration of the Oort cloud remains a distant goal, the data gathered by Voyager inspire new ideas about how such a mission might be achieved. Advances in propulsion technology and long-term power systems could one day enable spacecraft to reach and study the Oort cloud's icy bodies. Voyager's success in enduring the harsh conditions of space for more than 4 decades serves as a testament to the feasibility of long-duration missions. Voyager's silent partners, the Deep Space Network. Voyager's incredible journey through the solar system and into interstellar space is only possible because of a carefully designed partnership between the spacecraft and Earth. While Voyager probes tirelessly collect data billions of kilometers away, their connection to Earth is maintained by an often overlooked but essential system, the Deep Space Network. This global array of massive antennas ensures that the faint whispers of Voyager's signals, traveling across vast distances, can still reach us. The DSN is a network of radio antennas located at 3 strategic sites around the globe: Goldstone in California, Madrid in Spain, and Canberra in Australia. These locations are spaced roughly 120 degrees apart in longitude, ensuring continuous communication with spacecraft as the Earth rotates. Each site houses multiple antennas of varying sizes, with the largest dishes spanning 70 meters in diameter. These enormous structures are crucial for detecting the incredibly weak signals sent by Voyager, which are now far dimmer than any signal produced on Earth. Voyager's radio signal, transmitted at a power of just 20 watts, travels across billions of kilometers, spreading out and weakening as it goes. By the time it reaches Earth, the signal is so faint that it is measured in fractions of a billionth of a watt. Detecting this faint signal is akin to listening for the rustle of a leaf from thousands of kilometers away. The DSN's massive antennas, equipped with highly sensitive receivers, make this feat possible, acting as a bridge between humanity and the farthest reaches of space. The process of receiving Voyager's signal begins with the spacecraft's high-gain antenna, which directs its transmission toward Earth. This transmission is carefully timed and aimed, as even the smallest deviation in orientation could result in the signal missing its target entirely. The signal travels at the speed of light, taking nearly 24 hours to reach Earth from Voyager 1 and slightly less from Voyager 2. Upon arrival, the signal is captured by one of the DSN's antennas, which amplifies it and processes the data for scientists to analyze. The DSN's role goes beyond simply receiving signals. It also sends commands to Voyager. These commands are used to adjust the spacecraft's orientation, manage its instruments, and update its software as needed. Sending a command to Voyager is a delicate task, requiring precise calculations to ensure the message reaches the spacecraft at the correct time and location. Once the command is sent, there is a long wait for confirmation, as the round-trip communication time between Earth and Voyager is about 2 full days. As Voyager has traveled farther from Earth, the challenges of maintaining communication have grown. The spacecraft's power supply has diminished over time, reducing the strength of its transmissions. Additionally, the increasing distance means that the signal becomes fainter and takes longer to arrive. To address these challenges, the DSN has undergone upgrades, including the installation of more sensitive receivers and the addition of new antennas to improve coverage. The DSN's role in Voyager's mission is a testament to the importance of Earth-based infrastructure in space exploration. While spacecraft often capture the public's imagination, their success depends on the systems that support them from the ground. The DSN operates around the clock, with teams of engineers and technicians monitoring the antennas and ensuring they function flawlessly. Their work is essential for maintaining the delicate connection between Voyager and Earth, enabling the spacecraft to send back data that would otherwise be lost to the void. When the Voyager mission began in the 1970s, the DSN was already a sophisticated system, but it has continued to evolve over the decades. Advances in signal processing, such as the use of digital receivers and noise reduction techniques, have allowed the DSN to detect even fainter signals than originally anticipated. These innovations have extended the life of the Voyager mission, allowing it to continue providing valuable data long after its primary objectives were completed. The DSN's role is not limited to the Voyager mission. It supports a wide range of spacecraft, from Mars rovers to lunar orbiters and beyond. This versatility demonstrates the DSN's importance as a cornerstone of space exploration, enabling communication with spacecraft across the solar system. However, Voyager's incredible distance and faint signals make it one of the DSN's most challenging and rewarding missions. Each time the network successfully receives a signal from Voyager, it is a triumph of engineering and teamwork, a reminder of what can be achieved through collaboration and perseverance. Maintaining the DSN's operations requires a significant investment of resources and expertise. The antennas must be meticulously maintained to ensure they function optimally, and the equipment must be regularly updated to keep pace with advances in technology. The DSN's global network also requires coordination across multiple time zones and languages, highlighting the international nature of space exploration. Despite these challenges, the DSN continues to operate as a vital link between Earth and the cosmos, a bridge that connects humanity to the farthest reaches of space. The relationship between Voyager and the DSN is a partnership that underscores the interconnected nature of space exploration. While Voyager represents humanity's desire to reach out into the unknown, the DSN symbolizes the support and connection that make such journeys possible. Together, they have expanded our understanding of the solar system and beyond. Anticipating the future. Voyager's trajectory through the galaxy. These spacecraft, now freed from the confines of the solar system, are set to travel through the vastness of the Milky Way, offering a glimpse into their distant future as silent wanderers in a realm of stars, gas, and dust. While their instruments will eventually fall silent, their trajectories will carry them deeper into the galaxy, weaving through the fabric of interstellar space. Voyager 1, the faster of the two spacecraft, is heading in the direction of the constellation Ophiuchus. It is moving at a speed of about 17 kilometers per second relative to the Sun. In approximately 40,000 years, it will pass within 1.6 light-years of a star known as Gliese 445, located in the constellation Camelopardalis. Though it will not come close enough to significantly interact with this star system, this flyby underscores the immense timescales involved in interstellar travel. Voyager 2, traveling at a slightly slower pace, is heading toward the constellation Telescopium. In roughly 40,000 years, it will pass near a star called Ross 248, another red dwarf located about 10.3 light-years from Earth. Unlike its sibling, Voyager 2's trajectory is slightly tilted relative to the galactic plane, meaning it will experience a slightly different path as it moves through the galaxy. Over tens of thousands of years, the subtle gravitational influence of nearby stars and the Milky Way's overall mass distribution will alter its course, though not enough to bring it into direct contact with any celestial body. Both spacecraft are currently traveling through a relatively quiet region of interstellar space. This area, often referred to as the local interstellar cloud, is a pocket of material that the solar system is moving through. Composed mainly of hydrogen and helium, the cloud spans about 30 light-years and has a temperature of a few thousand degrees Celsius, about as hot as the surface of the Sun. Despite its high temperature, the density of particles is incredibly low, about 0.3 atoms per cubic centimeter. As Voyager continues its journey, it will eventually leave this cloud and enter other regions of interstellar space, each with its unique properties. The Milky Way's magnetic field is a complex, ever-changing structure that influences the motion of charged particles and cosmic rays. As Voyager travels deeper into interstellar space, it will move through regions where the magnetic field lines are oriented differently, potentially encountering turbulence or regions of stronger magnetic intensity. These interactions will not affect the spacecraft's trajectory significantly. Over hundreds of thousands of years, Voyager will continue to drift further from the Sun and the influence of its gravity. The spacecraft will eventually become true interstellar objects, traveling independently of any star. In this sense, they join the ranks of other celestial wanderers, such as rogue planets and interstellar asteroids, which roam the galaxy without a permanent home. Unlike these natural objects, however, Voyager carries the mark of its creators, a testament to human curiosity and ingenuity. The galaxy is not a static structure. It rotates, with stars and other objects orbiting its center. The Sun, along with the entire solar system, is currently located in a region known as the Orion Arm and orbits the galactic center at a speed of about 828,000 kilometers per hour. This motion means that Voyager is not just moving through interstellar space, but also participating in the grand rotation of the galaxy. Over millions of years, the spacecraft will follow this motion, tracing a spiral path around the Milky Way's core. As the spacecraft moves further from Earth, its signals will eventually become too faint to detect, marking the end of its active mission. However, the physical structure of Voyager will persist, protected by the vacuum of space. Without an atmosphere or significant radiation to degrade it, Voyager could remain intact for billions of years, outlasting not only the civilization that built it, but possibly even the Earth itself. In this distant future, Voyager may encounter other star systems, though the likelihood of a close approach is exceedingly small. The vast distances between stars make such encounters rare, even over billions of years. If Voyager were to pass near a star, it might be drawn slightly off course by its gravitational pull, altering its trajectory ever so slightly. This process, known as gravitational scattering, is a common phenomenon in the galaxy and has shaped the motion of countless objects over cosmic timescales. Both spacecraft carry a golden record designed to communicate the essence of humanity to any intelligent beings that might find it. While the chances of it being intercepted are vanishingly small, the mere possibility adds an element of wonder to Voyager's journey. If such a discovery were to occur, it would likely happen millions or even billions of years in the future, long after humanity has evolved or perhaps even disappeared. As Voyager continues its journey, it serves as a reminder of the vastness of the cosmos. The spacecraft's trajectory is a tiny thread in the immense tapestry of the galaxy, a path that stretches across unimaginable distances and timescales. Its journey inspires us to think beyond our immediate surroundings and consider our place in the universe. Interstellar travel. Lessons from Voyager's speed and longevity. The Voyager probes, though not designed as interstellar spacecraft in the modern sense, have taught us much about the realities of traveling through the vast distances of space. They are the first human-made objects to enter interstellar space, and their journey offers valuable insights into the challenges and possibilities of venturing beyond the solar system. Voyager's speed is one of its defining characteristics, yet it also highlights the immense scale of the universe. Traveling at approximately 17 kilometers per second, Voyager 1 is the fastest spacecraft ever launched. This speed is impressive by earthly standards, but it underscores how slow even our most advanced technology is when compared to the distances between stars. At its current pace, Voyager 1 would take tens of thousands of years to reach the nearest star system, Proxima Centauri, which lies about 4.24 light-years away. This sobering reality illustrates the challenge of interstellar travel. The vast distances involved make even our fastest spacecraft seem like they are crawling. Voyager's trajectory through space is measured not in years or centuries, but in millennia. For spacecraft like Voyager, the journey is essentially eternal, far exceeding the lifespan of the civilization that launched it. This introduces a profound challenge for future interstellar missions: how to design a spacecraft that can endure for such extended periods. Voyager's durability, achieved through careful engineering and robust materials, offers a glimpse of what might be possible, but also reveals the limitations of current technology. One of the key lessons from Voyager's longevity is the importance of simplicity and reliability. the spacecraft were built to last, with redundant systems and a focus on durability over complexity. Their power comes from nuclear sources, which convert heat into electricity. However, even this robust system is finite, and the Voyagers are expected to lose power completely within the next decade. Future interstellar missions will need to find ways to extend power supplies even further, possibly through advances in nuclear or solar energy technologies. Voyager's instruments and components were designed to withstand the harsh conditions of space, including extreme temperatures, radiation, and micrometeoroid impacts. The fact that both probes have continued to function for so long is a testament to the foresight and skill of their designers. However, the interstellar environment presents new challenges, such as exposure to higher levels of cosmic radiation and the potential for collisions with interstellar dust particles. These factors will need to be addressed in future spacecraft designs to ensure their survival over long journeys. Maintaining contact with a spacecraft billions of kilometers away requires an extraordinary level of precision and coordination. The Deep Space Network has made it possible to receive data from Voyager even as its signal has grown weaker over time. However, the delay in communication becomes a significant issue at interstellar distances. For Voyager, this delay is measured in hours, but for missions to other star systems, it could stretch to years. Future interstellar missions will need to incorporate autonomous systems that can operate independently of real-time instructions from Earth. Voyager's journey is a testament to human curiosity and the desire to explore, but its primary mission was focused on the planets of our solar system. Its interstellar phase is more of an epilogue than a primary objective. For future missions designed specifically for interstellar travel, the objectives will need to be carefully defined. Are we seeking to study the interstellar medium, to reach another star system, or to search for extraterrestrial life? Each goal will influence the design, trajectory, and technology of the spacecraft. Voyager's speed, while impressive, is insufficient for reaching other star systems within a human lifetime. Advanced propulsion technologies, such as nuclear fusion, antimatter engines, or light sails, are often proposed as potential solutions. These technologies could increase spacecraft speeds to a significant fraction of the speed of light, reducing travel times to decades or centuries rather than millennia. However, these concepts remain largely theoretical, requiring breakthroughs in physics, engineering, and energy generation. The data it has collected and transmitted to Earth is invaluable, but it is limited by the technology of its time. Future interstellar missions will need to incorporate more advanced sensors, data storage, and transmission capabilities to ensure that the information they gather can be preserved and understood by future generations. This further raises questions about how to encode and transmit data in a way that remains accessible and meaningful over centuries or millennia. The Voyager mission has benefited from the support of multiple generations of scientists, engineers, and technicians, as well as international partnerships. Interstellar missions will require even greater levels of collaboration, given their complexity, cost, and duration. They will also require a commitment to continuity, ensuring that the mission's goals and resources are maintained over the long term. Alien archaeology. Voyager as an artifact of humanity. If one day they are discovered by an advanced alien species, the spacecrafts would become artifacts of a distant civilization, pieces of archaeology floating in the cosmic sea. For those hypothetical finders, interpreting Voyager's construction and purpose might be their first glimpse into the existence of humans and our culture. It's a scenario that invites us to think about how we might appear through alien eyes. An alien species encountering Voyager would likely begin with its physical structure. The spacecraft's form, with its extended boom, parabolic antenna, and array of scientific instruments, might suggest its purpose as a machine built for exploration. The precision of its construction, the symmetry of its design, the use of metal alloys, and the organization of its components would indicate a technological species with a deep understanding of engineering principles. The materials used in Voyager, particularly the golden record cover and its etched diagrams, would also convey clues about the level of technological advancement achieved by its creators. The golden record itself, a 12-inch gold-plated copper disc, would likely stand out as the most intriguing feature of the spacecraft. Encased in its protective cover, the record bears markings that might initially appear cryptic, but are rich with meaning. The etched symbols, including the pulsar map and hydrogen atom diagram, are designed to provide universal references. For an advanced species familiar with these scientific constants, the map would indicate Voyager's origin, Earth, and its location in relation to nearby pulsars. The diagram of the hydrogen atom's transition might serve as a Rosetta Stone, offering a common ground for interpreting the record's content. An alien species capable of intercepting Voyager would presumably possess advanced technology and scientific understanding, but they might still face challenges in interpreting human symbols and intentions. The instructions for playing the record, etched onto its cover, include a representation of the record's grooves, a stylus, and the sequence for decoding the audio and visual data. These instructions assume a certain level of familiarity with mechanical playback systems, which might or might not align with the alien species' own technological paradigms. If the aliens succeeded in playing the record, they would be greeted by a curated selection of sounds and images chosen to represent the diversity of life and culture on Earth. The audio portion includes greetings in 55 languages, natural sounds like thunder and birdsong, and music ranging from Bach to Chuck Berry. The visual images, encoded as analog signals, depict scenes of human life, landscapes, animals, and scientific concepts. For an alien archaeologist, these recordings would offer a wealth of information to analyze. The variety of languages might suggest the presence of multiple cultures or nations on Earth, while the music could hint at emotional and artistic expression. The natural sounds and images would convey the richness of Earth's environment, its biodiversity, and its physical landscapes. Interpreting these messages would require the aliens to make assumptions about the context in which they were created. For example, they might wonder why certain images or sounds were chosen over others. The absence of more recent technological achievements, like digital devices or space-based infrastructure, might lead them to speculate about the timeline of human development. They might also ponder the meaning behind specific choices, such as the inclusion of a human heartbeat or the diagram of DNA. These elements, while scientifically significant to us, could be interpreted in entirely different ways by a species with their own unique perspective on biology and technology. The Golden Record also includes a symbolic message of goodwill, a representation of human aspirations to connect with others in the universe. For an alien species, this intent might be as fascinating as the content itself. They might interpret the record as evidence of a species capable of self-reflection and curiosity, one that sought to reach beyond its own planet despite the vast distances and challenges of interstellar space. The very act of sending Voyager might be seen as a statement about humanity's desire to explore, communicate, and leave a mark on the cosmos. Beyond the Golden Record, Voyager's scientific instruments and onboard systems would offer additional insights into human technology and priorities. The inclusion of devices like the plasma spectrometer, cosmic ray detector, and magnetometer might suggest a focus on understanding the physical properties of space. The spacecraft's power source, its radioisotope thermoelectric generators, could reveal knowledge of nuclear energy and its practical applications. Even the spacecraft's durability, its ability to survive harsh radiation, extreme temperatures, and the vacuum of space, might speak to the ingenuity and resilience of its designers. If Voyager were found in interstellar space, far from any star system, the aliens might deduce that it was launched intentionally with the goal of traveling beyond its point of origin. They might study its trajectory to determine the influence of gravitational assists from planets, piecing together its path through the solar system. This analysis could reveal the existence of a planetary system around the Sun and provide hints about the dynamics of our solar neighborhood. An alien species might wonder whether the spacecraft represents the entirety of human civilization, or just a fragment of it. They might speculate about the reasons for sending it into space, whether it was a gesture of curiosity, a call for contact, or an act of preservation. The absence of any direct communication capabilities might suggest that Voyager was not meant for two-way interaction, but rather as a one-sided message in a cosmic bottle. If the aliens had the capability to trace Voyager's origins, they might turn their attention to Earth. Depending on their technological reach, they might study our planet from afar, analyzing its atmosphere, surface features, and energy emissions for signs of life and activity. The data provided by Voyager, combined with their own observations, could create a mosaic of information about humanity and our world. The encounter with Voyager might provoke philosophical reflections among the alien species. They might consider the implications of finding evidence of another intelligent civilization, however distant in space and time. The spacecraft's simple yet profound message, a blend of science, art, and humanity, might resonate with their own experiences of exploration and discovery. Voyager, as an artifact, could become a symbol of the shared quest for understanding that transcends the boundaries of species and worlds. Voyager's role as an archaeological artifact underscores the enduring legacy of human curiosity and creativity. It is a testament to our desire to explore the unknown, to communicate across the void, and to leave a record of our existence for others to find. Has this deep dive into the remarkable Voyager spacecrafts inspired you as much as it has inspired us? What topic would you like for us to cover next? Send us your thoughts in the comments, and if you enjoyed the video, consider leaving a like and subscribing. Thanks for watching.